Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and the universe reveals itself at a pace gentle enough to drift alongside your thoughts. Tonight's quiet exploration takes us towards something both simple and strangely difficult to define. Brightness. Not just the kind that makes you squint on a sunny day, or the glow of a lamp in a dim room, but the kind that stretches across the vastness of space, the kind that travels for millions, even billions of years, just to arrive softly at your eyes. Somewhere out there, beyond the familiar stars, beyond even the galaxies we casually mention in documentaries, exist things so bright that they challenge the limits of what we can even imagine. And yet, here you are in your own small pocket of light, perhaps with a screen glowing gently in front of you, maybe a lamp nearby, maybe darkness all around except for this quiet voice and your thoughts. It's funny, isn't it? We talk about the brightest things in the universe while sitting in such a calm, dim, human-sized space. So, let me ask you something simple before we wander any further. Where are you listening from tonight? And what does the light look like around you right now? Is it soft and warm like the last glow of evening, or cool and artificial like a quiet room lit by a screen? Or maybe it's almost completely dark, the kind of darkness where even the smallest light feels important. If you find this kind of slow wandering through the universe relaxing or just a pleasant way to wind down, I'd really appreciate it if you gave the video a like and maybe subscribed. It helps this calm little corner reach more people who might need a quiet moment, just like this one. Now don't worry. This won't be one of those overwhelming journeys filled with numbers flying past and concepts rushing ahead. There's no need to keep up with anything. We'll take it slowly, step by step, like walking through a quiet place where every detail has time to settle. Because brightness, as it turns out, isn't just about intensity or power. It's about perception, distance, energy, and sometimes a bit of illusion. What looks bright to us isn't always the brightest thing out there, and what truly is the brightest? Well, it might not look that way at all from where we're sitting. Think about something familiar for a moment. A simple light bulb in a dark room. It doesn't take much for it to feel bright. Your eyes adjust, your surroundings fade into shadow, and suddenly that small source of light becomes the center of everything you can see. Now imagine stepping outside during the day under a clear sky. The same light bulb would seem almost invisible, completely overwhelmed by the sun. Not because it stopped shining, but because something vastly brighter took its place in your awareness. Already, without needing any equations or complicated physics, you can feel something important beginning to take shape. Brightness isn't absolute. It depends on what else is around, how far away something is, and how your eyes, or your instruments, or your mind interpret what's arriving. And this is where our journey really begins. Because when we ask, what is the brightest thing in the universe? We're not just asking for a single object, like pointing to the tallest mountain or the deepest ocean trench. We're stepping into a question that changes depending on how you look at it. Do we mean the brightest thing as it appears from Earth? Or the thing that actually produces the most light, regardless of distance? Or maybe the most intense flash ever observed, even if it only lasted a few seconds? Each of those answers could lead us somewhere completely different. So instead of rushing toward the answer, we'll take the same path your reference script gently followed. We'll start close to home, with what we know, what we see every day, and slowly, carefully expand outward. From the light you experience right now, to the light of our sun, to stars far larger and hotter, to explosions that briefly outshine entire galaxies, to objects so extreme they don't just shine, they reshape the space around them. And somewhere along that path, the idea of brightness will quietly shift from something simple into something far more surprising. But before we leave this moment behind, let's stay here just a little longer. Take a second, if you can, to notice the light around you again, the way it falls on surfaces, the way it fades into shadow, the way it feels more like a presence than a thing you can touch. because everything we're about to explore, from the smallest flicker to the most powerful burst in the universe, is ultimately just light, travelling, moving, arriving. And right now, in this exact moment, countless photons that began their journey somewhere far away are reaching you. Some from nearby sources, some from distant ones. Some might have been travelling longer than human history itself, all quietly arriving without announcement, becoming part of what you see. Which makes the question even more interesting. Out of everything that shines, out of everything that has ever released light into the universe, what truly stands at the very top? What is the brightest thing there is? Let's slow things down for a moment, because before we can even begin comparing stars, explosions, or distant cosmic objects, we need to understand something much closer to home. When you hear the word bright, what comes to mind? Maybe it's the sun on a clear day, forcing your eyes to narrow. Maybe it's a phone screen in a dark room, suddenly feeling much stronger than it really is. Or perhaps it's something softer, like a candle in the evening, which doesn't overwhelm you, but still draws your attention completely. What's interesting is that all of these feel bright in their own way, even though they are wildly different in actual power. And that's where things begin to get a little deceptive, because brightness, as we experience it, isn't just about how much light something produces. It's about how that light reaches us, how our eyes interpret it, and what we're comparing it to in that moment. Think about walking into a dark room after being outside in daylight. At first, everything seems almost completely black. You can barely make out shapes, and even the smallest light feels significant. But wait a minute or two, and suddenly the room begins to reveal itself. Objects appear, edges sharpen. That same faint light that seemed almost invisible before now feels noticeable. Nothing in the room changed. The light didn't get stronger. Your eyes simply adjusted. This is one of the first quiet clues that brightness is not an absolute experience. It's something your brain constructs based on context. Now consider the opposite situation. You're outside at midday under a bright sky. The sun is flooding everything with light. If you were to turn on a flashlight, even a reasonably strong one, it would barely be visible. It hasn't become weaker. It's still producing the same amount of light. But compared to the sun, it disappears into the background. So already, without needing any complex physics, we can say something important. Brightness is relative. It depends on what else is around. It depends on how sensitive your eyes are at that moment, and it depends on distance, which we'll come back to very soon. But let's stay with perception just a little longer, because your brain plays a surprisingly large role in this story. Your eyes don't measure brightness like a scientific instrument. They don't give you exact numbers or precise readings. Instead, they adapt, constantly adjusting to make sure you can see as much detail as possible in different conditions. This ability is incredibly useful. It allows you to function in bright sunlight and dim environments without needing to think about it. But it also means your sense of brightness is always shifting. A candle can feel bright in darkness. The moon can feel bright in the night sky, and yet both of those are incredibly faint compared to the sun. In fact, the full moon, which can light up landscapes and cast shadows, is roughly 400,000 times dimmer than sunlight, and still, to us, it feels luminous, even powerful in its own quiet way. So if our perception can be so easily influenced, then how do scientists define brightness? Well, they don't rely on feeling. They rely on measurement. But even here, things aren't as simple as they first appear. There are actually different ways to talk about brightness, depending on what exactly you mean. One way is to ask, how bright does something appear from where we are? This is called apparent brightness. It's the brightness you would measure if you stood here on Earth and looked at an object. It includes all the effects of distance, spreading, and anything that might weaken the light before it reaches you. For example, the sun appears extremely bright to us, far brighter than any star in the night sky. But that doesn't mean it's the most powerful star out there. It just means it's very close. Now there's another way to think about brightness, Instead of asking how bright something looks, we can ask how much light it actually produces. This is called intrinsic brightness, or luminosity. It's a measure of the total energy an object emits as light, regardless of how far away it is. And this is where things start to become a little more surprising, because many of the stars you see at night, the tiny points of light scattered across the sky, are actually far more powerful than the sun. They just appear faint because they are so far away. It's a bit like seeing a distant lighthouse across the ocean. From where you stand, it might look like a small, dim flicker, but up close, it could be overwhelmingly bright. So when we ask about the brightest thing in the universe, we have to be careful. Are we talking about what appears brightest to us, or what truly produces the most light? Those are two very different questions, and we're mostly interested in the second one, the true, underlying brightness, not just what happens to reach us here on Earth. But even that isn't the full story, because brightness doesn't just depend on how much light is produced, it also depends on how that light spreads out. Imagine holding a flashlight in your hand. If you shine it directly at a wall a meter away, the light is concentrated in a small area, and it appears bright. But if you step back several meters, the same light spreads out over a larger area, and it becomes dimmer. The flashlight hasn't changed. It's still producing the same amount of light, but that light is now spread thinner. This is a very important idea, and it applies to everything in the universe. Light doesn't stay concentrated as it travels. It spreads out in all directions like ripples on the surface of water, and as it spreads, it becomes less intense. This is why distant objects appear dim, even if they are incredibly powerful. In fact, the relationship between distance and brightness follows a very simple rule, though we'll keep it gentle here. If you double the distance from a light source, the brightness doesn't just drop a little, it drops significantly. By the time you're much farther away, even the brightest objects can appear faint. So when you look up at the night sky and see a star that seems small and dim, you're not necessarily looking at something weak. You might be looking at something unimaginably powerful, just very, very far away. And this brings us to a quiet but important realization. The universe is full of things that are far brighter than they appear, which means that answering our original question isn't just about looking up and picking the brightest point we can see. It's about uncovering what's really happening behind the scenes. What's producing the most light? What's releasing the most energy? And how do we even begin to compare things that exist on such different scales, from stars to explosions to entire galaxies? Before we can move outward into those extremes, it helps to establish a kind of baseline, something familiar that we can use as a reference point. Because without that, everything else becomes a bit abstract. Take a moment to picture the last time you stepped outside on a clear day, not rushing anywhere, not checking your phone, just standing there for a second. The light would have been everywhere, filling the sky, bouncing off buildings, softening edges, making everything visible without effort. It's so constant, so reliable, that most of the time we don't even notice it. And yet, that steady presence above you, the sun, is by far the brightest thing you encounter in your everyday life. Not just a little brighter than anything else, but overwhelmingly, almost absurdly brighter. It's the reason your eyes narrow when you look toward the sky, the reason shadows form sharply beneath objects, the reason colours exist at all during the day. Without it, everything would fade into darkness almost instantly. But because it's always there, rising and setting with quiet consistency, it doesn't feel extreme, it feels normal, which is perhaps the most interesting thing about it. Because if you could somehow step outside your daily experience and see the sun as it truly is, not as a familiar part of your routine, but as an object in the universe, you might find it far more impressive than it first seems. Let's ease into that idea gently. The sun is a star. That part is well known. But it's not just a glowing ball sitting in the sky. It's an enormous, active, constantly changing sphere of hot plasma, producing energy at a rate that's difficult to grasp in everyday terms. Every second, deep in its core, hydrogen atoms are being fused together to form helium. This process, nuclear fusion, releases an immense amount of energy that begins as intense radiation in the sun's centre and slowly works its way outward, eventually escaping into space as light. Some of that light travels in your direction, and after about 8 minutes of crossing the vast distance between the sun and Earth, it arrives here, spreading out across the planet, warming the surface, lighting the sky, making life possible. That 8-minute journey is already a small hint of scale. Light, which moves faster than anything else in the universe, still takes time to get here. And yet, even after travelling that distance, the sun's light is still powerful enough to dominate everything you see. In fact, if you compare it to the moon, which can feel quite bright on a clear night, the difference is staggering. Sunlight is hundreds of thousands of times more intense than moonlight. And if you compare it to the stars you see at night, the difference becomes almost hard to describe. Those stars might look like tiny points, faint and distant, but many of them are actually similar to the sun, or even much larger and more powerful. They only appear dim because they are unimaginably far away. The sun, by contrast, is close enough that its brightness overwhelms everything else in the sky during the day, close enough that it defines our entire sense of what bright means in daily life. But here's something worth sitting with for a moment. The sun feels bright not just because of what it is, but because of where we are. If you could move the sun farther away even slightly, it would begin to lose its dominance. The sky would dim, shadows would soften. Eventually it would look just like another star, one among many, no longer special to your eyes. And if you could move closer, the brightness would increase dramatically. The heat would rise. The light would intensify beyond anything comfortable or survivable. So once again, we find ourselves returning to that idea. Brightness depends on distance. The sun is incredibly powerful, yes, but its apparent brightness, the way it feels to us, is amplified by proximity. It's like sitting next to a campfire. Up close, it feels intense, almost overwhelming. Step back, and it becomes gentle. Move far enough away, and it becomes just a faint glow. The fire hasn't changed, only your position has. Now, there's another quiet detail about the sun that often goes unnoticed. It shines in all directions, not just toward Earth, not just toward the planets, but outward in every possible direction, sending light into space where no one is there to see it. Most of the energy it produces never reaches anything at all. It simply travels onward, into the vastness, which means that even something as bright and powerful as the sun is, in a way, constantly wasting most of its light. It doesn't focus its brightness, it doesn't aim, it simply shines. And this matters, because when we start looking for the brightest things in the universe, we'll discover objects that behave very differently. Some concentrate their energy, some release it in bursts, some produce light in ways that don't resemble stars at all. But for now, the sun gives us a useful reference point. It tells us what a star can do. It shows us how brightness can feel when you're close to the source. And it reminds us that what seems overwhelmingly bright in our daily experience might not be the upper limit of what the universe can produce. In fact, the sun is not even among the most powerful stars. There are stars larger, hotter, and far more luminous. Stars that release many times the energy of our sun every second. If one of those replaced the sun in our sky, the difference wouldn't be subtle. It would be immediate and dramatic. And yet, even those stars are just one step along a much larger scale. Because brightness in the universe doesn't stop with stars. It continues beyond them, into events and objects that push energy to levels far beyond what a stable star can maintain. Before we move any further outward into the universe, it helps to pause and look at something so familiar that it almost disappears from notice. Light. Not just as a glow or a brightness, but as something that actually travels. Something that moves through space, something that begins somewhere and ends somewhere else. Because everything we've been talking about so far, from the sun to distant stars, only reaches you because light carries that information across the emptiness. And once you start to think of light as something moving rather than just something present, the whole idea of brightness begins to shift slightly. Let's keep this simple and grounded. At its most basic level, light is energy. It doesn't need air, it doesn't need a medium, it doesn't need anything to carry it. It can move through complete emptiness, across space where there's nothing at all, and still arrive exactly where it's going. That alone is already a little unusual. Most things we're familiar with need something to travel through. Sound needs air, waves need water, but light doesn't. It crosses the vacuum of space without slowing down, without getting tired, without losing its identity. And it does this at a speed that's difficult to relate to in everyday life. Light travels at about 300,000 kilometers per second. That's fast enough to circle the entire Earth more than 7 times in a single second. If you could somehow chase a beam of light, even at unimaginable speed, you would never quite catch it. But here's where things become a little more interesting. Light doesn't travel as a continuous stream in the way we might imagine, like water flowing from a tap. Instead, it comes in tiny packets of energy called photons. You can think of photons as little messengers. Each one carries a small amount of energy, and when many of them arrive together, we perceive that as brightness. So when you look at a light source, what you're really seeing is a constant stream of these photons arriving at your eyes. The more photons that reach you in a given moment, the brighter something appears. Fewer photons, and the light looks dim. This idea connects very naturally to what we talked about earlier. If something is close, more of its photons reach you. If it's far away, those photons spread out, and fewer of them arrive. Nothing magical is happening to the light itself. It's simply becoming more spread out over distance. Imagine tossing a handful of tiny glowing particles into the air. Close to where they were thrown, they're dense and easy to see. But as they spread outward, they become more scattered, harder to notice, even though the total number hasn't changed. Light behaves in a similar way, except it spreads in all directions, not just across a surface, and that spreading is one of the main reasons distant objects look dim. But there's another layer to this that's worth noticing. Not all photons are the same. They can carry different amounts of energy, and that energy determines what kind of a light we're dealing with. Some photons carry just enough energy to be visible to your eyes, forming the colours you recognise from red through to violet. Others carry more energy, becoming ultraviolet light, X-rays or even gamma rays, and some carry less, becoming infrared or radio waves. So when we talk about brightness, we're usually talking about visible light, the narrow range your eyes can detect. But in reality, the universe is filled with light across a much wider spectrum, much of it invisible to you. There are objects that don't appear especially bright in visible light, but are incredibly powerful in other forms of radiation. And that complicates our question even further, because something might not look bright to your eyes, but could still be releasing enormous amounts of energy in forms of light you can't see. So brightness, once again, depends on how you measure it. What kind of light are you looking at? What part of the spectrum are you considering? And what instrument are you using to detect it? Your eyes are just one kind of detector, and a fairly limited one at that. Now let's bring this back to something more intuitive. Imagine standing in a gentle rain. Each raindrop is like a photon. If the rain is light, only a few drops hit you each second. If it becomes heavy, more and more drops arrive and you feel the increase immediately. Brightness works in a similar way. A bright source sends out an enormous number of photons, and if you're in the path of that stream, many of them reach you every second. A dim source sends out fewer, or its photons are more spread out by the time they arrive. But unlike rain, photons don't slow down or fall. They move in straight lines at constant speed, continuing their journey until something interacts with them. That interaction is what allows you to see. When photons reach your eyes, they are absorbed by cells in your retina, which convert that energy into signals your brain can interpret. That's when light becomes an image, when brightness becomes something you experience. Until that moment, it's just energy travelling, which means that everything you see right now is a kind of delayed message. The light from your surroundings left its source a fraction of a second ago. The light from the sun left about 8 minutes ago. The light from distant stars left years, centuries, or even longer ago. You're not seeing things as they are right now. You're seeing them as they were when their light began its journey toward you. And this becomes especially important when we start looking at the brightest things in the universe, because some of the light we observe from distant objects has been travelling for millions or even billions of years. Which means we're not just looking at brightness, we're looking at history. Now there's one more quiet detail about light that will matter later. Light doesn't just carry energy, it also carries information. The colour of the light tells us something about the temperature of its source. The intensity tells us something about how much energy is being released. Subtle shifts in the light can even tell us whether something is moving toward us or away from us. So when scientists observe distant objects, they're not just seeing brightness, they're decoding it, using light as a kind of message that reveals what's happening far away. And sometimes those messages describe things far more powerful than anything we experience in daily life. But for now, we can keep it simple. Light is energy, travelling through space, carried by photons, spreading out as it moves, and eventually reaching us where it becomes something we can see. And brightness, at its core, is simply about how much of that energy arrives. Now that we've taken a gentle look at what light actually is, it becomes a little easier to understand something that quietly shapes almost everything we see in the universe. Distance. Not just as a number, not just as how far something is, but as something that actively changes how light behaves by the time it reaches you. Because when light leaves a source, whether it's a candle, a star, or something far more extreme, it doesn't travel in a neat, narrow line. It spreads outward in all directions, expanding into space as it moves, and that spreading changes everything. Let's keep this grounded in something simple. Imagine you're holding a small flashlight in a dark room. If you point it at a wall just one step away, the light forms a bright, concentrated spot. It feels strong, clear, and easy to see. Now take a few steps back. The same flashlight, the same amount of light, is now spread across a wider area. The spot becomes larger, softer, less intense. Step even farther back, and eventually the light fades into the darkness. It hasn't stopped shining. It hasn't become weaker. It's simply spread out so much that each small part of it carries less intensity. This is one of the most important ideas in understanding brightness. Light spreads, and as it spreads, it becomes less concentrated. In the universe, this spreading happens in 3 dimensions, not just across a wall, but outward in all directions, like a sphere expanding from its source. You can picture it like ripples on water, except instead of staying on the surface, they move outward in every direction, forming an ever-growing bubble of light. Close to the source, that bubble is small, and the light is dense. Far away, that bubble is enormous, and the same amount of light is spread thin. So even if something is incredibly powerful, producing an enormous amount of light, it can still appear faint if you're far enough away from it. This is why distance changes everything, and it leads to something that can feel a little counterintuitive at first. 2 objects can produce vastly different amounts of light, but if one is much farther away, they might appear equally bright. Or even more surprising, the weaker object could appear brighter simply because it's closer. Think about the night sky. When you look up, the stars seem small, quiet, almost delicate. Tiny points scattered across a dark background. It's easy to assume they're all relatively modest sources of light, but that impression is misleading. Many of those stars are far larger and far more powerful than the sun. Some release many times the energy every second. Some are so luminous that, if placed where the sun is now, they would completely transform the sky, making daylight far more intense than anything we experience. And yet, from where we stand, they appear as faint pinpricks. Not because they are weak, but because they are unimaginably far away. Now here's something worth pausing on. If you could somehow move closer to one of those distant stars without changing anything else, just reducing the distance, its brightness would increase dramatically. Not gradually, but quickly. Because the relationship between distance and brightness isn't gentle, it's steep. If you double your distance from a light source, the brightness doesn't just drop by half, it drops much more than that. And as you continue to move away, the brightness falls off faster and faster. This is why the universe can feel so calm and quiet when you look at it from Earth. Distance softens everything. It smooths out extremes. It takes things that are incredibly powerful and reduces them to something that feels manageable, even peaceful. But that calm appearance is in many ways an illusion created by space itself. Now let's bring this idea a little closer to everyday experience again. Imagine you're standing on a hill at night, looking at a city far away. The lights might appear as a soft glow on the horizon, not particularly intense, just a gentle shimmer. But if you were to travel toward that city, the lights would grow brighter, sharper, more distinct. Eventually you'd find yourself surrounded by them, no longer seeing a distant glow, but individual sources, each one contributing to the overall brightness. The city didn't change, only your distance from it did. The same thing is happening when you look at the universe. You're seeing everything from a very particular position, very far from most of what's out there. And because of that, even the brightest objects can appear subdued. Now there's another subtle effect of distance that's worth noticing. Not only does light spread out, but over very large distances, especially across the scale of the universe, light can also be affected by the expansion of space itself. As the universe expands, the light travelling through it can be stretched, its wavelength becoming longer. This shifts it toward the red end of the spectrum, something known as redshift. We don't need to go deeply into that here, but it's another way distance can change what we perceive. It doesn't just dim light, it can alter it. So when scientists observe distant objects, they have to account for all of this. They can't simply look at how bright something appears and take that at face value. They have to ask, how far away is it? How much has its light spread out? Has its light changed during its journey? Only then can they begin to estimate how bright it truly is. And when they do that, the results can be surprising. Objects that look faint can turn out to be incredibly powerful. Events that appear small can be releasing enormous amounts of energy. The quiet night sky, which seems so still and gentle, becomes something much more active and dynamic when you understand what's really happening behind the scenes. So when we ask about the brightest thing in the universe, we can't rely on appearances. We can't just look up and choose what seems brightest. We have to look deeper. We have to correct for distance. We have to imagine what these objects would look like if we were closer, if we could see them without the softening effect of space. And when we do that, the scale of brightness begins to expand far beyond what we experience in daily life. Step outside on a clear night, and for a moment everything feels quiet. The sky stretches above you, dark and still, dotted with small points of light that seem calm, almost gentle. There's nothing overwhelming about it. No harsh brightness, no sense of intensity, just a soft scattering of stars, each one flickering faintly against the darkness. It doesn't feel extreme. It doesn't feel powerful. If anything, it feels peaceful. And yet, almost everything you're looking at in that moment is far more intense than it appears. This is one of the most subtle illusions we live with every day. The night sky looks quiet, but it isn't. It looks faint, but it isn't. It looks small, but it absolutely isn't. Let's stay with that feeling for just a second. Imagine you're lying on your back looking up. The stars seem close enough to count, like tiny points placed carefully on a dark surface. There's no sense of depth, no obvious scale, just a flat, calm scene. But that flatness is an illusion created by distance. In reality, those stars are scattered across vast three-dimensional space. Some are relatively close, at least in cosmic terms. Others are much farther away, their light travelling for hundreds or thousands of years before reaching you. And yet your eyes compress all of that into a single quiet view. Everything appears equally distant. Everything appears equally small. This is the first part of the illusion. Your brain simplifies what it sees. It takes something unimaginably large and turns it into something manageable. Now let's think about brightness again, just for a moment. When you look at those stars, they don't seem particularly bright. Even the most noticeable ones are still gentle compared to the sun, or even the moon. You can look at them directly without discomfort. Some are so faint that you have to focus carefully just to notice them. It's easy to assume they must be relatively modest sources of light. But that assumption is almost always wrong. Many of the stars you see are producing enormous amounts of energy. Some are similar to the sun, some are far larger, far hotter, and far more luminous. Some release tens of thousands of times more energy than the sun every second, and still they appear as tiny faint points. Why? Because of distance. The same principle we talked about earlier is quietly at work here. Their light has travelled such enormous distances that by the time it reaches you, it has spread out so much that only a tiny fraction of it enters your eyes. You're not seeing the star as it is. You're seeing a very small sample of what it produces, and that changes your entire perception. To make this a bit more intuitive, imagine a powerful spotlight shining in the distance. Up close, it would be intense, almost blinding. But if you move far enough away, it becomes just a small point, something you can look at comfortably. The power hasn't changed, only your position has. Now extend that idea to distances so large that even light moving at incredible speed takes years to cross them. That's what you're dealing with when you look at the night sky. Now there's another layer to this illusion that's worth noticing. Your eyes have limits. They can only detect a certain range of brightness, and they're not particularly good at capturing faint light compared to the instruments scientists use. So when you look up, you're not seeing everything that's there. You're seeing only the stars bright enough to cross that threshold. There are many more stars, far more than you can see, but they're too faint from your perspective, which means the night sky isn't just dimmed by distance, it's filtered. You're seeing a carefully reduced version of reality, shaped by both distance and the sensitivity of your eyes. If you were to use a telescope, even a small one, the sky would immediately change. More stars would appear. Dim points would become clearer. The illusion of emptiness would begin to fade, and with larger telescopes the change becomes even more dramatic. Regions of the sky that look almost empty to the naked eye suddenly reveal dense fields of stars, galaxies, and structures far beyond what you could ever notice without assistance. It's like turning up the brightness on a screen and discovering there was far more detail hidden in the shadows than you realized. So the calm, sparse sky we experience is not the full picture. It's a softened version, a distant version, a version shaped by limitations. Now here's something that quietly changes how you might think about all of this. Every star you see is not just far away, it's also in the past. The light reaching you tonight didn't leave those stars just now. It left years ago. In some cases, decades, centuries or more. Which means you're not just looking at distant objects, you're looking at old light. And that adds another layer to the illusion. Because what you're seeing may not even represent the star as it is today. It represents how it was when that light began its journey. Some stars may have changed since then. Some might even no longer exist in the same form. And yet their light continues to arrive quietly, steadily, giving the impression of a stable, unchanging sky. So the night sky is not just distant, it's delayed, it's filtered, it's compressed, and all of that combines to create the sense that what you're seeing is calm, faint, and simple. When in reality, it's none of those things. It's active, it's powerful, and in many cases, it's far brighter than anything we experience in our daily lives. Now, once you begin to see through this illusion, something interesting happens. Those small points of light stop feeling quite so small. They become hints of something larger, signals from objects that are far more intense than they appear. If you take the sun as your reference point, it feels like a reasonable standard. It lights your entire day, warms the planet, shapes the sky, and quietly powers almost everything around you. It's easy to assume that it must be one of the more impressive stars out there. After all, it does quite a lot. But as it turns out, the sun is not especially extreme. It's stable, reliable, and well-behaved, which is exactly what makes life possible here. But in terms of raw brightness, there are many stars that go far beyond it, releasing far more energy every second, shining more intensely and living much more dramatic lives. And once you begin to look at those stars, the scale of brightness starts to stretch in a way that feels almost surprising. Let's ease into that gently. Stars shine because of what's happening deep inside them. Just like the sun, they are powered by nuclear fusion, where lighter elements are combined into heavier ones, releasing energy in the process. But not all stars are the same size. And size matters. A star that is more massive than the sun has more material, more pressure at its core and higher temperatures. That means fusion happens faster, more intensely, and releases more energy. So a bigger star doesn't just shine a little brighter, it can shine many times brighter. Now imagine a star several times the mass of the sun. Its core is hotter, its energy output much greater, and its surface temperature higher. Instead of the sun's familiar warm yellow-white glow, these stars can appear bluish, indicating much higher temperatures. These are often called blue giants or blue supergiants, and they are among the brightest stable stars in the universe. If one of these stars replaced the sun in our sky, the difference wouldn't be subtle. Daylight would become far more intense, shadows would sharpen, the sky itself might take on a different tone, and depending on how close you were, the conditions on Earth would become difficult, to put it gently. But let's not rush ahead, because what really matters here is the comparison. The sun produces an enormous amount of energy every second, but a blue giant can produce tens of thousands, sometimes even hundreds of thousands of times more, and yet when you look at the night sky, those stars don't stand out in a dramatic way. They don't dominate your vision the way the sun does during the day. They appear small, quiet, faint. Once again, distance is doing its work. Now there's another type of star worth mentioning, one that takes things even further. Some stars grow to truly enormous sizes, becoming what are known as supergiants or hypergiants. These stars can be hundreds of times larger than the sun in diameter. To picture that, imagine placing the sun at the centre of the solar system. A star of that size could extend outward, past the orbit of Earth, and sometimes even beyond. But here's the interesting part. Being larger doesn't always mean being brighter in the way you might expect. Brightness depends not just on size, but also on temperature. Some of these enormous stars are cooler on the surface, giving them a reddish appearance. Others are both large and extremely hot, making them incredibly luminous. So the brightest stars are usually those that combine both high temperature and significant size. Hot, massive, and energetic. Now let's pause on something that might feel a little counterintuitive. Even though these stars are far brighter than the sun, they don't last as long. In fact, the brighter a star is, the faster it tends to burn through its fuel. It's a bit like a fire. A small steady flame can last for a long time. A large intense blaze burns quickly, consuming its fuel at a much faster rate. So while the sun can shine for billions of years, many of these brighter stars live much shorter lives, sometimes only millions of years. In cosmic terms, that's relatively brief, so brightness in a way comes at a cost. The more energy a star releases, the faster it moves through its life. Now let's bring this back to something visual again. When you look at the night sky, some stars do stand out a little more than others. A few appear brighter, more noticeable. But even those are still only giving you a small hint of what they really are. Because what you're seeing is the result of two things combined, their true brightness and their distance. A star might appear bright because it's relatively close. Another might appear dim because it's extremely far away, even if it's far more powerful. So appearances can be misleading. And this is something that keeps repeating as we move through the universe. The most powerful things are not always the most obvious. Sometimes they're hidden behind distance. Sometimes their light arrives quietly, softened by the journey. Now, there's one more detail about these brighter stars that's worth noticing before we move on. They are not just brighter, they are more dynamic, more unstable, more prone to dramatic endings. Because the same conditions that make them shine so intensely, high mass, high temperature, rapid fusion, also push them towards something much more energetic at the end of their lives. They don't fade quietly. They don't simply dim over time. Instead, many of them end in events that release enormous amounts of energy in a very short period. And when that happens, for a brief moment they can outshine not just other stars but entire galaxies. There comes a point in the life of certain stars when steady shining is no longer enough. For a long time, they live in balance. Outward pressure from the energy in their core pushes against the inward pull of gravity. It's a quiet equilibrium, one that can last millions or even billions of years depending on the star. But that balance doesn't last forever. Eventually, something begins to change. The fuel in the core starts to run low, and the processes that once held everything stable begin to weaken. Gravity, which has been patiently pulling inward the entire time, starts to take the lead. And when that happens, the star doesn't simply fade away, it reacts. Sometimes gently, but sometimes in a way that releases more energy in a few moments than the star produced over its entire lifetime. This is what we call a supernova, and it's one of the most dramatic events in the universe. Let's take this slowly because it's easy to picture it as just an explosion, something quick and chaotic like a firework in the sky. But it's more than that. It's the final act of a star that has spent its entire existence building toward this moment. In some cases, the core of the star collapses suddenly under its own gravity. The outer layers, no longer supported, fall inward and then rebound outward in a powerful shockwave. In other cases, especially in systems where stars exist in pairs, matter can be pulled from one star onto another, building pressure until a sudden runaway reaction occurs. Different paths, but a similar result, an enormous release of energy. Now here's where things begin to stretch beyond anything familiar. For a brief period, a supernova can outshine an entire galaxy. Not just a few stars, not just thousands, but billions of stars combined. And it does this in a matter of days or weeks. If you pause on that for a moment, it starts to feel a little difficult to picture. A single star ending its life, suddenly becoming brighter than the combined light of countless others. And yet, from Earth, these events don't always look overwhelming. They appear as a new point of light in the sky, sometimes brighter than usual, sometimes even visible during the day if they're close enough. But rarely do they feel as intense as they truly are. Once again, distance softens everything. A supernova that is unimaginably bright at its source can still appear as just a bright star to us, because its light has travelled so far, spreading out along the way. But even from that distance, the effect can be noticeable. There are records from human history of supernovae appearing suddenly in the sky, bright enough to be seen in daylight, lingering for weeks before fading away. To the people who witnessed them, these must have felt mysterious, unexpected, almost unsettling. A new star appearing where none had been before, then slowly disappearing. Now, let's bring this back to brightness in a more grounded way. A typical star like the Sun produces a steady output of energy over a very long time. A supernova, on the other hand, releases an enormous amount of energy in a very short time. So while the Sun shines consistently, a supernova briefly becomes far more luminous. It's not about lasting brightness, it's about peak brightness. For those moments, it becomes one of the brightest things in the universe. But only for a while. That's an important detail. Supernovae don't last. They fade. The explosion expands outward. The energy disperses and the brightness gradually diminishes. What remains behind depends on the original star. Sometimes it leaves a dense core, like a neutron star. Sometimes it collapses further into something even more extreme. But the intense brightness, the part that briefly outshines everything around it, is temporary. Now, there's another quiet aspect of supernovae that connects back to everything we've discussed so far. They don't just produce visible light, they release energy across a wide range of forms: radiation, particles, shock waves, all moving outward into space. So when we talk about their brightness, we're often focusing on the visible part, the light we can detect easily. But the total energy involved is even greater, and this begins to push us toward a broader understanding of brightness. It's not just about what we can see, it's about total energy output. How much energy is being released, and how concentrated that release is over time. And supernovae show us that brightness can come in bursts, not just steady shining, but sudden, powerful flashes. Now, if you imagine being close to such an event, which is something we're quite fortunate not to experience, the brightness would be overwhelming. It wouldn't feel like a star in the sky. It would feel like something much closer, much more immediate. But from where we are, safely distant, we see only a softened version, a bright point, a temporary addition to the sky. Another reminder that what we observe is always shaped by where we stand. So, as impressive as supernovae are, and they are incredibly impressive, they are not the final step in this story. Because even these massive explosions are not the most extreme sources of brightness. There are events that release energy in even more concentrated ways, shorter, sharper, more intense. Moments where brightness doesn't just increase, but spikes to levels that are difficult to compare with anything else. If you take a step back for a moment and think about the sun again, not just as something familiar, but as a source of energy, it already feels like a reasonable upper limit. It lights an entire planet. It warms oceans, drives weather, fuels life, and has done so continuously for billions of years. Every second it releases an amount of energy that is difficult to put into everyday terms. Even a small fraction of that energy reaching Earth is enough to sustain everything around you. So it's natural to assume that something this powerful must sit fairly high on the scale of brightness. And yet, when we place the sun next to a supernova, the comparison becomes almost difficult to hold in your mind. Because the difference isn't just large, it's extreme. Let's take this slowly, in a way that doesn't rush past the scale. The sun shines steadily. Every second, it releases energy at a consistent rate, driven by the fusion happening in its core. That process is stable, controlled, and long-lasting. It's designed, in a sense, to maintain balance. And that's exactly what makes it dependable. But a supernova is not about balance. It's about release. It's what happens when a star can no longer maintain that steady state, when the forces that once kept everything in equilibrium suddenly give way, and energy that has been building up is unleashed in a very short span of time. So instead of a steady output stretched over billions of years, a supernova compresses an enormous amount of energy into days, weeks, or months. Now imagine trying to compare those two things: a slow, steady flow, and a sudden, overwhelming surge. One way to think about it is this: if the sun were a steady stream of water flowing from a tap, then a supernova would be like releasing an entire reservoir all at once. The total amount of water might be comparable over very long periods, but the rate at which it's released is completely different, and it's that rate, that concentration of energy in a short time, that makes a supernova so incredibly bright. Let's make this a bit more tangible. The sun produces energy continuously, second after second, year after year. Over its entire lifetime, it will release an enormous total amount of energy. But a supernova, in just a few weeks, can release as much energy as the sun will produce over its entire lifespan, not in billions of years, in weeks. And that's where the scale starts to stretch. Because when that much energy is released in such a short time, the brightness increases dramatically. it doesn't just become brighter than the sun, it becomes vastly brighter. For that brief period, a single supernova can outshine all the stars in its host galaxy combined. Not just one star, not just a cluster, an entire galaxy. Now, it's worth pausing here because that statement can feel abstract. A galaxy contains billions of stars, each one producing its own light, each contributing to the overall glow, and yet for a short time, one event can surpass all of that. If you could somehow observe a galaxy from a distance and watch a supernova occur within it, you would see a sudden increase in brightness, a new point of light that stands out sharply against everything else. It would feel like something unexpected had appeared, something that didn't quite match the steady rhythm of the stars. Now, from Earth, we don't experience this in an overwhelming way, because again, distance softens everything. Even an event of this scale, happening far away, appears as a bright but manageable point of light, something noticeable but not blinding, something that can be observed without discomfort. And that's a quiet reminder of how much distance shapes our perception. Because if you were much closer, the experience would be very different. The brightness would not feel gentle, it would not feel distant, it would dominate everything. But from here, we see only a reduced version. Now, there's another layer to this comparison that's worth noticing. The sun's energy is spread out over time. It's consistent, predictable, and long-lasting. A supernova's energy is concentrated. It arrives quickly, peaks, and then fades. So when we talk about brightness, we're really talking about intensity over time. How much energy is being released and how quickly. And in that sense, a supernova is one of the most intense events a star can produce, but is also temporary. After the explosion, the brightness declines, the expanding material cools, the light fades, and what remains is something very different from what was there before. This is important because it highlights a pattern that keeps appearing as we move through this topic. Some of the brightest things in the universe are not stable, they don't last. They appear briefly, shine intensely, and then disappear or transform. Brightness in these cases is tied to change, to transition, to moments when something shifts from one state to another. Now let's return to something more familiar again, just to keep the comparison grounded. Imagine standing outside during the day feeling the warmth of sunlight. That warmth is the result of energy that has travelled millions of kilometres to reach you. It's steady, reliable, and comfortable. Now imagine that same location, but instead of the sun's steady output, you suddenly receive an enormous burst of energy all at once, not gradually, not over hours, but concentrated into a short moment. The difference wouldn't just be noticeable, it would be overwhelming. That's the difference between steady brightness and explosive brightness, and it's why supernovae stand out as some of the most luminous events in the universe, even though they don't last long. But even here, we're not at the end of the scale, because as powerful as supernovae are, there are events that go even further, shorter in duration, more concentrated, releasing energy in ways that push beyond what even a supernova can achieve. And before we move to those, it helps to sit with this comparison just a little longer. The sun represents stability, a long, steady release of energy, a reliable source of light that shapes our daily lives. A supernova represents intensity, a brief, powerful release that outshines almost everything around it. Two very different expressions of brightness, two very different timescales, and both of them are part of the same story. A story where brightness isn't just about how much light something produces, but how that light is delivered. Slowly, or all at once. What if the most extreme brightness doesn't come from stars themselves, but from what's left behind after they collapse? What if the most intense light doesn't come from something stable, or even from something exploding, but from something much smaller, much denser, and far more unusual than anything we've looked at so far? After something as dramatic as a supernova, it might feel like we've already reached the upper limits of brightness. A star collapsing, exploding, briefly outshining an entire galaxy. It sounds like the kind of event that would sit comfortably at the top of any scale, and yet what's left behind after that explosion can be just as fascinating, and in some ways, even more extreme. Not larger, not louder, but denser, more concentrated, more focused in the way it releases energy, because when certain massive stars reach the end of their lives and collapse, they don't simply scatter everything into space and disappear. Instead, their core compresses into something incredibly small, incredibly dense, and unlike anything we encounter in everyday experience. This is what we call a neutron star. Now, let's approach this slowly, because it's one of those ideas that can feel abstract if you jump straight to the numbers. Imagine taking something the size of the sun, a massive sphere of hot plasma stretching across more than 1 million kilometers, and compressing it down into something only about the size of a city. Not a continent, not a country, a city. The amount of matter stays roughly the same, but the space it occupies becomes drastically smaller, and when that happens, everything changes. Gravity becomes incredibly strong, density becomes almost unimaginable, and the behaviour of matter itself starts to shift into something far removed from what we're used to. Inside a neutron star, the pressure is so intense that atoms can no longer exist in their usual form. Electrons are pushed into protons, forming neutrons. What you're left with is a kind of matter that is packed together so tightly that a small amount of it would weigh more than anything you could realistically picture lifting or holding. But for now, we don't need to focus too much on the exact details of that structure. What matters for our journey is what this means for brightness. Because even though a neutron star is much smaller than a normal star, it can still release an enormous amount of energy. And it does so in a very different way. Unlike the sun, which shines steadily through fusion, a neutron star is more like a leftover core, incredibly hot, incredibly dense, and often spinning very rapidly. Some of them rotate many times per second. Imagine something the size of a city spinning faster than a kitchen blender, carrying an immense amount of energy in that motion alone. Now add to that extremely strong magnetic fields, far stronger than anything we can produce on Earth. These magnetic fields can guide and channel energy in specific directions, creating beams of radiation that extend outward into space. And this is where things start to become particularly interesting. Because even though a neutron star might not shine uniformly in all directions like the sun, it can emit very intense beams of energy. If one of those beams happens to sweep across your line of sight, you would observe it as a regular pulse of light. On, off, on, off! These objects are known as pulsars, and we'll explore them more closely in just a moment. But even before we get there, it's worth sitting with this idea. A neutron star is small compared to a typical star. And yet, because of its density, its temperature, its rotation, and its magnetic fields, it can still be incredibly bright in certain ways. Not necessarily as a constant, all-encompassing glow, but as something focused, intense, and sometimes even rhythmic. Now, let's bring this back to the comparison we've been building. The sun shines steadily, spreading its light in all directions. A supernova releases a massive burst of energy in a short time. A neutron star, on the other hand, represents something more concentrated. Its energy is not spread gently across a vast surface, it's compressed into a much smaller space. And that concentration allows for very intense emissions, even if the total output over time is different. It's a bit like comparing a wide, soft light to a narrow, focused beam. The total energy might not always be greater, but the intensity in a specific direction can be much higher. And that intensity is another way of thinking about brightness. Because brightness isn't just about total output, it's also about how that output is distributed. Now there's another detail that quietly adds to the picture. Neutron stars are incredibly hot when they first form. The The collapse that creates them releases a tremendous amount of energy, heating the remaining core to extremely high temperatures. Over time they cool down, but in their early stages they can be very luminous, and even as they cool, their magnetic fields and rotation can continue to drive energetic emissions. So they don't simply fade away, they continue to interact with their surroundings, releasing energy in different forms. Now imagine being close to such an object. Not close enough to be affected by its gravity in a dangerous way, but close enough to observe its brightness directly. The experience wouldn't feel like looking at a normal star. It would feel sharper, more intense in specific directions, more focused, especially if you happen to be in the path of one of its beams. But from Earth, once again, distance changes everything. Most neutron stars are far away. Their light, like everything else we've discussed, spreads out over vast distances before reaching us. So what we observe is a softened version, a signal that arrives as pulses, a pattern that repeats, a hint of something much more intense at its source. And this pattern is what makes pulsars so useful to scientists, because their regular pulses can be measured with incredible precision, almost like cosmic clocks. But beyond their usefulness, they also represent another step in our exploration of brightness. They show that brightness doesn't always come from size, it doesn't always come from steady output. Sometimes it comes from concentration, from density, from the way energy is directed and released, and this is where the story begins to shift again. Because if a small, dense object can produce such intense emissions, what happens when we take this idea even further? What happens when gravity becomes even stronger? When energy is concentrated even more? And when the processes involved push beyond what we've seen so far? Something begins to feel a little different when brightness stops behaving like a steady glow. Up to this point, most of what we've talked about has followed a familiar pattern. A star shines in all directions. A supernova bursts outward. Even the sun, for all its power, spreads its light evenly, without preference, without rhythm. But now imagine a source of light that doesn't shine continuously in every direction. Instead, it sweeps, it rotates, it pulses, appearing, disappearing, appearing again with a kind of precision that feels almost intentional, even though it isn't. This is where pulsars come in. They are not a completely new kind of object. They are neutron stars, the same dense remnants we just explored. But they behave in a very specific way that makes them stand out, not just as sources of light, but as something much more structured. To ease into this, picture a lighthouse. Not the modern kind with bright electric beams, but a classic one, standing on a rocky coastline. Its light doesn't fill the entire horizon at once. Instead, it rotates, sending a narrow beam across the sea. If you're standing in the path of that beam, the light appears suddenly bright and clear, then it passes and darkness returns. Then a few seconds later, it comes back again. On, off, on, off. The lighthouse hasn't changed. It's still emitting light continuously, but because the beam is focused and rotating, your experience of it becomes rhythmic. That's the key idea behind pulsars. A pulsar is a rapidly spinning neutron star with a strong magnetic field, emitting beams of radiation from its poles. As it spins, those beams sweep across space, and if one of those beams crosses Earth, we detect it as a pulse. Not because the star is turning on and off, but because the beam is moving in and out of our line of sight. Now, let's slow down and unpack that just a little. When a neutron star forms, it often inherits the rotation of the original star. But because it has collapsed into something much smaller, that rotation speeds up dramatically. It's a bit like a figure skater pulling in their arms to spin faster. The size decreases, the speed increases, so a neutron star that might have once rotated slowly can end up spinning many times per second. Some pulsars rotate dozens, even hundreds of times per second, which means their beams sweep across space with incredible speed and regularity. Now add to that the magnetic field. Neutron stars have extremely strong magnetic fields, far beyond anything we can create here on Earth. These fields channel charged particles and energy along specific paths, focusing the emission into beams. So instead of light spreading evenly in all directions, much of the energy is directed along these beams, and that changes how brightness works, because when energy is focused rather than spread out, it becomes more intense in that direction. It's like the difference between a bare light bulb and a spotlight. The bulb spreads light everywhere. The spotlight concentrates it into a narrow beam, making it appear much brighter within that beam, even if the total energy isn't greater. Pulsars behave more like that spotlight, and this is why they can be so striking. From Earth, a pulsar might not look especially bright in a general sense, but when its beam sweeps past us, the signal we detect can be very strong, very precise, and incredibly regular. Some pulsars are so consistent that their pulses can be measured with extraordinary accuracy, almost like a ticking clock. In fact, for a long time, their regularity was so surprising that when they were first discovered, scientists briefly wondered if they might be artificial signals, something designed, something intentional. But of course, they are natural, just an elegant result of physics working under extreme conditions. Now, let's bring this back to our ongoing question about brightness. Because pulsars show us something important. Brightness isn't just about how much energy is produced, it's also about how that energy is directed. A star like the Sun spreads its energy in all directions, which means any single point receives only a small fraction of it. A pulsar, by contrast, concentrates much of its energy into narrow beams, so if you happen to be in the path of that beam, the intensity you observe can be very high. But if you're outside that path, you might see very little at all, which means brightness, once again, depends on position, where you're relative to the source, whether you're inside the beam or outside it. And that adds another layer to the idea we've been building. Brightness is not just about the object, it's about the relationship between the object and the observer. Now, there's another detail that quietly makes pulsars even more interesting. They don't just emit visible light. In many cases, they emit radiation across a wide range of wavelengths, including radio waves, X-rays, and gamma rays, which means that their true energy output is not always obvious if you're only looking with your eyes. In fact, many pulsars were first detected using radio telescopes, picking up signals that would be completely invisible otherwise. So once again, we're reminded that what we see is only part of the picture. The universe is far more active, far more energetic than it appears at first glance, and pulsars are a perfect example of that. From a distance, they might seem like faint, distant objects, but in reality, they are compact, rapidly spinning sources of focused energy, sending out beams that can be detected across vast distances. Now imagine, just for a moment, being closer to one, not dangerously close, but close enough to experience its beam directly. The brightness wouldn't feel constant. It would come in pulses, sharp, regular flashes of energy sweeping past you again and again. It wouldn't feel like standing under sunlight. It would feel more like being near something mechanical, something precise, something repeating with perfect timing. And that sense of rhythm is what makes pulsars feel different from everything we've looked at so far. They don't just shine, they signal, they mark time, they sweep across space like quiet beacons. But even with all of this, even with their focused beams and intense emissions, pulsars are still not the brightest things in the universe. They are part of a pattern we've been following. Each step introduces something more concentrated, more extreme, more intense in how it releases energy. At this point, brightness has already taken on several different forms. We've seen it as something steady, like the sun, spreading its light gently in all directions. We've seen it as something explosive, like a supernova, releasing enormous energy in a short burst. And we've seen it as something focused, like a pulsar, sending beams that sweep across space with precise rhythm. Each step has added a new layer. Each has stretched the idea a little further. But now we arrive at something that doesn't quite fit into any of those categories. Something that is not just bright for a moment, not just bright in a narrow beam, but sustained, immense, and visible across distances so vast that even light takes billions of years to reach us. These are quasars, and among them, one of the most extreme examples we know today is J0529-4351. Now, let's ease into this carefully, because quasars can sound abstract at first. The name itself comes from quasi-stellar object, meaning something that looked like a star when first observed, but didn't behave like one. Through early telescopes, they appeared as small points of light, not much different from distant stars. But when scientists began to study them more closely, they realized something didn't add up. They were far too distant, and yet far too bright. So bright, in fact, that they could be seen across billions of light years, which immediately raises a question. What kind of object could produce that much light and keep doing so continuously? Because unlike a supernova, which fades, quasars persist. They shine steadily, often for millions of years. So where does that energy come from? The answer takes us somewhere we've only hinted at so far. At the centre of most galaxies, including our own, there exists something incredibly massive, a black hole. Not the kind that quietly sits in isolation, but one surrounded by matter, gas, dust and debris slowly falling inward. And as that material spirals toward the black hole, something remarkable happens. It doesn't just fall in directly. Instead, it forms a swirling disk around the black hole, known as an accretion disk. Now imagine that disk not as something calm, but as something incredibly active. The material within it is moving at enormous speeds, colliding, compressing, heating up as it spirals inward. Friction builds, temperatures rise, energy is released, and as a result, the disk begins to glow, not softly, not gently, but intensely. In fact, the light produced by this process can outshine all the stars in the galaxy combined, not for a moment, but continuously, and that glowing region, powered by matter falling into a supermassive black hole, is what we observe as a quasar. So in a way, the brightness of a quasar doesn't come from a star. It comes from the process of matter being pulled towards something that doesn't even emit light itself. A black hole, which we often think of as completely dark, becomes the centre of one of the brightest phenomena in the universe. And that's already a bit of a shift in how we think about brightness, because here, brightness is not about fusion. It's not about a star burning. It's about motion, gravity and energy being released as matter falls inward. Now, let's bring this back to J0529-4351. This object is one of the brightest quasars ever discovered. It lies at an enormous distance from Earth, billions of light years away, which means the light we see from it today began its journey long before anything like human civilization existed. And yet, even after travelling that distance, it is still detectable, still measurable, still standing out among countless other sources. That alone tells you something about its scale. Because if distance softens brightness, and something remains visible across such vast space, then its original output must be extraordinary. And in this case, it is. The black hole powering this quasar is incredibly massive, billions of times the mass of the Sun. And the accretion disk surrounding it is releasing energy at a rate that dwarfs anything we've discussed so far. If you were to place something like this closer, not dangerously close, but even at a fraction of its current distance, it would dominate the sky completely. It wouldn't look like a star. It would look like something else entirely. A concentrated, blazing source of light, outshining everything around it. But from where we are, it appears small. Once again, distance shapes perception. Now, there's another detail that makes quasars particularly interesting when we talk about brightness. They don't just emit light in all directions equally. In many cases, they also produce powerful jets of energy that extend outward from the poles of the black hole. These jets can travel vast distances, carrying energy far beyond the immediate region of the accretion disk. And in some orientations, if one of those jets points toward us, the observed brightness can increase even further. So once again, direction matters, position matters. Brightness is not just about what is produced, but how it is distributed and where you happen to be relative to it. Now, let's pause here for a moment and look at the pattern that's been forming. We started with the Sun, a steady source of light. We moved to larger, hotter stars producing more energy, then to supernovae, releasing energy in sudden bursts, then to neutron stars and pulsars, concentrating energy into smaller spaces and focused beams, and now to quasars, where gravity itself becomes the engine of brightness, pulling matter inward and converting that motion into light on a scale that spans entire galaxies. Each step has taken us further. Each has expanded what we mean by bright. And yet, even here, we're not necessarily at the final answer. Because while quasars like J0529-4351 are among the brightest sustained sources of light we know, there are still events that can briefly surpass them. Not in duration, not in steady output, but in intensity over very short timescales. Moments where the universe releases energy and flashes so powerful that they outshine almost everything else, even if only for seconds. So the story continues. Brightness, it seems, is not just about one kind of object. It's about different ways energy can be released, steadily, explosively, or in sudden concentrated bursts. There's something quietly puzzling about quasars when you first encounter them. Not just how bright they are, but how they manage to stay that bright. A supernova, as we've seen, releases an enormous amount of energy, but only for a short time. It peaks, fades, and eventually settles into something quieter. Pulsars emit focused beams, but their total output, while intense in specific directions, doesn't quite reach the same sustained scale. Quasars, though, are different. They don't just flare. They endure. They shine steadily for long periods, sometimes millions of years, maintaining a level of brightness that can outshine entire galaxies. And that raises a very natural question. Where does all that energy come from? Because if you imagine something producing that much light continuously, your first instinct might be to think of something like a star, only larger, only hotter, only more powerful. But quasars are not stars. They are powered by something else entirely. To understand that, we need to slow things down and look at what's happening at the centre of a galaxy. Most galaxies, including our own, have a supermassive black hole at their core, not a small one, not something the size of a collapsed star, but something millions or even billions of times the mass of the Sun. Now, when you hear the term black hole, it's easy to picture something completely dark. Something that swallows everything, gives nothing back, and in a sense that's true. A black hole itself does not emit light, but the region around it can become one of the brightest places in the universe, and the reason for that lies in how matter behaves as it approaches the black hole. Let's imagine this gently. Picture gas, dust, and debris drifting through space near the centre of a galaxy. Over time, gravity pulls this material inward toward the black hole, but it doesn't fall straight in. Instead, it begins to spiral. As it moves closer, it forms a rotating disk around the black hole. This is the accretion disk. Now this disk is not calm, it's not smooth. It's a place of constant motion, where particles are moving at enormous speeds, orbiting faster and faster as they get closer to the centre. And as they move, they interact, they collide, they compress, friction builds, temperatures rise. And this is where the energy comes from. Because as the material in the disk is compressed and heated, it begins to glow. Not faintly, not gently, but intensely. In fact, the temperatures in parts of the accretion disk can become so high that they emit radiation across a wide range of wavelengths, including visible light, X-rays, and more. So the brightness of a quasar is not coming from the black hole itself, it's coming from the material around it. Material that is being accelerated, heated and energized as it spirals inward, Now, there's something particularly interesting about this process. It's extremely efficient. When a star produces energy through fusion, only a small fraction of its mass is converted into energy over time. But when matter falls into a black hole, the process of converting gravitational energy into radiation can be much more efficient. A significant portion of the energy associated with that matter's motion can be released as light before it crosses the point of no return. Which means that, in terms of energy output, this process can surpass what a star can achieve. So even though a black hole is often described as something that consumes, the process of feeding it can create an enormous amount of light. Now, let's pause here and connect this back to brightness. Because what we're seeing is another shift in how brightness is produced. It's no longer about fusion inside a star, it's about motion and gravity. It's about matter falling inward and releasing energy as it does so. And because this process can continue as long as there is material available, a quasar can remain bright for a long time. Not forever, but long enough to be observed across vast distances. Now, there's another detail that adds to the picture. The accretion disk is not the only source of energy in a quasar. In many cases, powerful jets of particles are launched from regions near the black hole's poles. These jets can travel enormous distances extending far beyond the galaxy itself, and they carry energy with them. So a quasar is not just a bright disk, it's a system, a central black hole surrounded by a glowing disk, with energy flowing outward in multiple forms, and depending on how this system is oriented relative to us, what we observe can vary. If we're looking at it from one angle, we might see the disk clearly. From another, we might detect strong emissions from the jets. Once again, brightness depends on perspective. Now, let's bring this back to something more intuitive. Imagine water flowing down a steep slope. As it moves, it accelerates, gains energy, and if it encounters obstacles, it can splash, churn, and release that energy in visible ways. The steeper the slope, the more energy is involved. Gravity is doing the work. In a quasar, something similar is happening, but on a much larger scale. Matter is falling into an incredibly deep gravitational well. As it does, it accelerates, heats up, and releases energy. That energy becomes light. So in a sense, a quasar is powered by gravity. Not directly, but through the motion it creates. And that's a subtle but important shift, because it means that some of the brightest things in the universe are not powered by burning, but by falling. Now, there's one more detail worth noticing before we move on. Quasars are not evenly distributed across time. Most of the quasars we observe come from the distant universe, meaning we are seeing them as they were billions of years ago. This suggests that quasars were more common in the earlier universe, when galaxies were still forming, and there was more material available to feed their central black holes. Over time, as that material was used up or dispersed, many quasars became less active. So when we observe something like J0529-4351, we're not just seeing a bright object, we're seeing a phase in the life of a galaxy, a period when its central black hole was actively feeding and producing enormous amounts of energy. And that adds another layer to the idea of brightness. It's not just about the object itself, it's about the conditions that allow that brightness to exist. Now, as powerful as quasars are, and they are among the brightest sustained sources we know, they're still part of a broader spectrum, because brightness, as we've been discovering, can come in different forms: steady, explosive, focused, and sometimes incredibly brief but even more intense. So the question naturally continues: if quasars represent one of the most powerful sustained sources of light, is there anything that can surpass them, even if only for a moment? At this stage, brightness has already stretched far beyond anything that feels familiar. We've moved from the steady glow of the sun, to stars that burn hotter and brighter, to supernovae that briefly outshine galaxies, and then to quasars, where entire regions around black holes radiate immense energy for millions of years. So it might feel like we've already reached the upper edge of what the universe can do. But there's a particular object that quietly pushes that idea even further, not by introducing a completely new mechanism, but by taking everything we've just explored and scaling it up to an extreme. This is TON 618. And to understand why it stands out, it helps to approach it slowly, without rushing straight to the numbers. Because what makes this object remarkable isn't just that it's bright, it's how consistently and how overwhelmingly it produces that brightness. Now, we've already seen how quasars work. A supermassive black hole sits at the centre, surrounded by an accretion disk of material spiralling inward. As that material accelerates, heats up, and interacts, it releases enormous amounts of energy. That process alone is enough to produce brightness that can outshine entire galaxies. But in the case of TON 618, everything about that setup is pushed further. The black hole at its centre is not just massive, it is extraordinarily massive, billions of times the mass of the Sun. So large, in fact, that even among supermassive black holes, it stands out as one of the most extreme examples we've observed. And that matters, because the mass of the black hole influences how much material it can pull in, how fast that material moves, and how much energy is released in the process. More mass means a deeper gravitational well. A deeper gravitational well means matter falls faster, compresses more, heats more, and releases more energy before crossing the boundary where it can no longer escape. So the brightness of a quasar is closely tied to how actively its black hole is feeding. And in this case, the feeding process is intense. Matter is continuously drawn in, forming a massive energetic accretion disk that radiates across vast distances. Now let's bring this back to something we can picture. Imagine a whirlpool in water. As water spirals inward, it speeds up, becoming more energetic, more turbulent, more active. Now scale that up, not just in size, but in energy. Replace water with gas and dust. Replace the gentle pull of gravity with something far stronger. And imagine the entire system glowing as energy is released. That's a rough way to think about what's happening around TON 618. Except, of course, the scale is far beyond anything we experience. Now here's where the idea of brightness becomes particularly striking. Even though this object is located billions of light years away, meaning its light has travelled for an immense amount of time to reach us, it is still detectable, still measurable, still standing out among countless other sources, and that tells you something important. Because as we've seen, distance reduces brightness. Light spreads out, becomes less concentrated, and appears dimmer. So if something remains visible across such a vast distance, its original output must be extraordinary. And in this case, it is. If you could somehow place TON 618 closer, not dangerously close, but closer than it currently is, it would dominate the sky completely. It wouldn't appear as a point. It would appear as something overwhelming, a source of light so intense that it would outshine everything else, not just stars, but entire regions of the sky. But from where we are, it appears small. Once again, distance softens the experience. Now, there's another detail that makes this object particularly interesting when we talk about the brightest thing, because brightness can be measured in different ways. We've already touched on apparent brightness, how bright something looks from Earth, and intrinsic brightness, how much energy it actually produces. Objects like TON 618 are important, because they rank extremely high in intrinsic brightness. They are among the most luminous sustained objects we know, not brief flashes, not momentary bursts, but continuous powerful sources of light, and that places them near the top of one version of our question. If we ask, what is the brightest thing that shines continuously for long periods, then objects like this are strong candidates. But as we've already begun to notice, brightness is not just about sustained output. There are events that release more energy in shorter bursts, moments that exceed even these massive steady systems, but only for a brief time. So once again, we find that there isn't a single, simple answer. There are different kinds of brightest. Steady brightness, explosive brightness, focused brightness, and each of them tells a different part of the story. Now, let's return to the experience for a moment, because everything we've discussed, all of these immense objects, all of this energy, is happening far away, far beyond our direct experience, and yet the light from these objects still reaches us. It travels across space, over immense periods of time, and arrives quietly, becoming part of what we can observe, which means that when you look up at the sky, even though you don't see something like TON 618 directly with your eyes, its light is still part of the universe you're connected to, a signal, a message, something that has travelled an incredible distance just to be detectable, and that adds a certain calm perspective to all of this, because even the brightest things in the universe, even the most extreme sources of light, are still subject to the same simple rule. Their light spreads, it travels, it softens, and by the time it reaches us, it becomes something we can observe without being overwhelmed. Trying to describe something as unimaginably bright is a little tricky, not because the word is wrong, but because it quietly admits something before we even begin, that whatever we're about to talk about doesn't fit neatly into everyday experience, and that's exactly where we are now. Up to this point, we've built a kind of ladder. We started with the sun, something familiar, something we can feel and see every day. Then we moved to stars that outshine it, then to supernovae that briefly surpass entire galaxies, and then to quasars like TON 618, which sustain enormous brightness over long periods. Each step made sense, because it was connected to the one before it. But now we reach a point where the comparisons begin to stretch, where numbers alone don't help much, where saying something is brighter stops being intuitive. So instead of relying on numbers, it helps to think in terms of scale and contrast. Let's return to something simple for a moment. Imagine a single candle in a completely dark room. It feels bright. Not overwhelming, but enough to define the space around you. Now replace that candle with a light bulb. The brightness increases. The room becomes clearer. Shadows become sharper. Now step outside into daylight. The sun takes over completely. The light bulb, which felt bright indoors, becomes almost invisible. Already we've moved through several levels of brightness that feel distinct and easy to understand, but everything we've just described is still within a very narrow range compared to what exists in the universe. Now imagine something that makes the sun feel like that candle, not in a poetic sense, in a literal physical sense, something that produces so much energy that, if placed nearby, it would dominate the sky far beyond anything we've ever experienced. This is the level we're approaching. But even that comparison only goes so far, because unimaginably bright doesn't just mean brighter than the sun, it means brighter than our entire collections of stars, brighter than galaxies, and sometimes brighter than anything else happening in the observable universe at that moment. Now, here's where things become a little more subtle. Brightness, as we've been building, depends on how energy is released, and there are different ways to achieve extreme brightness. One is to produce a large amount of energy steadily over time, like a quasar. Another is to release a vast amount of energy in a very short time, like a supernova. And there's a third way, which combines intensity and concentration, releasing enormous energy in a very focused, very brief burst. When that happens, the peak brightness can exceed almost everything else, even if it doesn't last. So when we say unimaginably bright, we're often referring to peak brightness, how intense something becomes at its most extreme moment. And that's where the scale becomes difficult to picture, because our experience of brightness is tied to gradual changes. We move from dim to bright in steps, candle to bulb, bulb to sunlight, sunlight to something slightly stronger. But the universe doesn't always follow that pattern. Sometimes it jumps, suddenly, from something manageable to something far beyond. Now, let's ground this again. Imagine standing under the sun, feeling its warmth, seeing how it lights everything around you. Now imagine increasing that intensity, not gradually but dramatically. Not doubling it, not increasing it 10 times, but increasing it by factors so large that the comparison stops being intuitive. At that point, it's no longer something you can comfortably relate to. It becomes something you can only describe indirectly, and that's why we use phrases like unimaginable. Not because it's completely beyond understanding, but because it doesn't map neatly onto anything we've experienced. Now, there's another quiet detail that helps make sense of this. When something becomes extremely bright, it often does so at a cost. It doesn't last. The more intense the release of energy, the shorter the duration tends to be. This is something we've already seen with supernovae, and it becomes even more pronounced as we move further. So unimaginably bright often means brief. A moment of extreme intensity, followed by a rapid decline, which adds another layer to the idea. Because brightness isn't just about how much energy is released, it's about how quickly it's released. Now let's bring this back to the bigger picture we've been building. We've seen steady brightness in stars, explosive brightness in supernovae, sustained, large-scale brightness in quasars, and now we're approaching something even more concentrated. Events that release energy so quickly, so intensely, that for a brief moment they become the brightest things in the universe. Even brighter than quasars, even brighter than anything sustained. But only for seconds. And that's where the idea of unimaginably bright becomes most relevant. Because when something releases more energy in a few seconds than the sun will produce over its entire lifetime, the comparison stops being comfortable. It stops being something you can scale up step by step. It becomes something that exists on a different level entirely. Now, here's something worth noticing before we move on. Even these extreme events, even the most intense bursts of brightness, are still subject to the same rules we've been following. Their light spreads, it travels, it softens over distance. So by the time it reaches us, it becomes something we can detect, measure, and study. Which means that even the most extreme brightness in the universe can be observed without overwhelming us, simply because of how far away it is. And that's a quiet kind of balance. The universe can produce incredible extremes, but distance ensures that we experience them in a manageable way. It might seem a little contradictory at first. A black hole, by definition, is something that does not let light escape. It's often described as completely dark, a region where gravity is so strong that nothing, not even light, can get out once it crosses a certain boundary. So how can something like that be associated with some of the brightest objects in the universe? How can something that is, in a sense, invisible, end up creating so much light that it outshines entire galaxies? The answer lies not in the black hole itself, but in everything happening just outside it. And to understand that, it helps to let go of the idea of a black hole as a simple, empty void. Instead, think of it as the center of a very active environment, because a black hole doesn't just sit alone in space, it pulls. Everything around it, gas, dust, stray material, even entire stars if they get too close, feels that pull. And as matter begins to move toward the black hole, something important happens. It doesn't fall straight in. Not usually. Instead, it begins to spiral, and that spiral is where the brightness begins. Let's imagine this slowly. Picture a wide, rotating disk of material forming around the black hole. This is the accretion disk we touched on earlier, but now we'll spend a little more time with it. The material in this disk is moving incredibly fast. Closer to the black hole, it moves faster still, and as it moves, it doesn't do so smoothly. Particles collide. They rub against each other, they compress. All of this motion creates friction, and friction creates heat. Now, in everyday life, friction might warm your hands or heat up a surface slightly, but here the conditions are far more extreme. The speeds are enormous, the pressures are intense, and the result is that the material in the disk heats up to temperatures that can reach millions of degrees. At those temperatures, it doesn't just glow, it radiates intensely. Across visible light, across X-rays, across other forms of radiation. So even though the black hole itself remains dark, the region around it becomes one of the brightest places in the universe, and that brightness comes from motion, from matter falling inward and releasing energy as it does so. Now, there's another layer to this that makes it even more interesting. As material moves closer to the black hole, the gravitational pull becomes stronger. This means that the energy involved in that motion increases. It's a bit like something falling from a great height. The deeper the fall, the more energy is released when that motion is converted into heat or impact. In the case of a black hole, the fall is incredibly deep. The gravitational well is steep, so the energy released as matter moves inward is enormous. And before that matter crosses the point where it can no longer escape, much of that energy is converted into radiation, into light. So the brightness of a quasar, or any actively feeding black hole, is not coming from inside the black hole, it's coming from the edge, from the last moments before matter disappears from view. Now, there's something else that adds to this picture: magnetic fields. Just like neutron stars, black holes can be surrounded by strong magnetic fields, especially in the regions where matter is moving rapidly. These fields can channel energy in specific directions, they can accelerate particles, they can even help launch powerful jets that extend far beyond the immediate area around the black hole. And these jets can carry enormous amounts of energy. In some cases, they stretch for thousands of light years, emitting radiation along the way. So the brightness we associate with black holes is not just coming from the disk, it's also coming from these outflows, these streams of energy being directed outward. Now, let's pause for a moment and bring this back to something more intuitive. Imagine water swirling down a drain. As it gets closer to the center, it speeds up. The motion becomes more intense. If you could somehow capture the energy of that motion, you would find that it increases as the water moves inward. Now replace that simple system with something far more extreme. Replace water with gas and plasma. Replace the drain with a black hole. And imagine that instead of disappearing quietly, the motion of that material is converted into light before it reaches the center. That's a simplified way of thinking about what's happening. But it captures the essence. Brightness, in this case, comes from falling, from motion, from energy being released as matter is pulled inward. Now there's a subtle point here that connects back to everything we've been building. Brightness is not just about what something is, it's about what's happening. A black hole by itself is dark, but a black hole that is actively pulling in material becomes a source of intense light, so the same object can be associated with both extremes, darkness and brightness, depending on its surroundings. Now let's bring this back to the larger picture again. We've seen that stars produce light through fusion. We've seen that supernovae release energy through collapse and explosion. We've seen that neutron stars and pulsars concentrate energy through density and rotation. And now we see that black holes can produce brightness through gravity and motion. Each step introduces a different mechanism, a different way of turning energy into light, and each one pushes the idea of brightness further. But even here, we're not at the end. There's a moment just before a camera flash goes off where everything feels still. Then suddenly, for a fraction of a second, the entire scene is flooded with light. Brighter than anything around it, sharp, immediate, impossible to ignore. And then, just as quickly it's gone, leaving only a fading afterimage. Now imagine something like that. But not in a room, not even on a planetary scale. Imagine it happening somewhere out in the universe, releasing more energy in a few seconds than the sun will produce over its entire lifetime. That's what we call a gamma-ray burst. And in many ways, these are the closest things we have to the idea of a flashbulb on a cosmic scale. Up to now, we've seen brightness in several forms: steady, like stars; explosive, like supernovae; sustained and immense, like quasars powered by black holes. But gamma-ray bursts introduce something different. They are not just bright. They are intensely, briefly, overwhelmingly bright, and then they're gone. Let's approach this slowly, because like many things we've explored, the scale can feel distant if we rush. Gamma ray bursts, often shortened to GRBs, are short-lived events that release enormous amounts of energy in the form of gamma rays, the highest energy form of light. These bursts can last anywhere from a fraction of a second to several minutes. That's it. Seconds. Minutes at most. And yet, in that time, they can outshine almost everything else in the observable universe. Now, the first thing to notice is that we're no longer talking about visible light. Gamma rays are far beyond what your eyes can detect. They carry much more energy than visible photons, which means that when we talk about brightness here, we're talking about total energy output, not just what you could see if you were looking directly at it. And that's important, because some of the most extreme brightness in the universe happens outside the range of human vision. Now, where do these bursts come from? There are a couple of main scenarios, and both are connected to events we've already touched on. One type of gamma ray burst occurs when a massive star collapses at the end of its life. Not just collapsing quietly, but forming a black hole in the process. As the core collapses, material around it forms a disk and begins to fall inward, much like what we see in quasars. But instead of producing a long-lasting source of light, this process creates powerful jets that shoot outward from the poles of the forming black hole. These jets are incredibly focused and incredibly energetic. If one of those jets happens to be pointed toward Earth, we detect it as a gamma ray burst. Another type of gamma ray burst comes from something even more compact, the collision of two neutron stars. Remember those dense remnants we talked about earlier? When two of them orbit each other closely, they can eventually merge, and when they do, the energy released is enormous. Again, powerful jets can form. Again, if one of those jets is aligned with us, we see a burst. So in both cases, the key idea is the same. Energy is being released in a very focused direction, not spread evenly in all directions like a star, but concentrated into narrow beams. And that concentration is what makes gamma ray bursts so extreme. Because when energy is focused, the intensity along that direction increases dramatically. Now, let's bring this back to something more intuitive. Imagine a hose spraying water. If the water is allowed to spread out, it forms a gentle flow. But if you narrow the nozzle, the same amount of water becomes a strong, focused jet. It travels farther, it hits harder, it feels more intense. Gamma ray bursts are like that, but with energy instead of water. The total energy involved is enormous, but because it's concentrated into narrow jets, the intensity along those jets becomes extraordinary. Now here's where things start to stretch beyond anything we've discussed so far. A gamma ray burst can release in a few seconds as much energy as the sun will emit over its entire lifetime. Let's pause on that. Billions of years of steady energy production, compressed into seconds. That's the level of intensity we're dealing with. And yet, from Earth, these events don't appear overwhelming. They don't light up the sky in a visible way. They don't suddenly turn night into day, because they are so far away, and because most of their energy is not in visible light. Instead, we detect them using specialized instruments that can observe gamma rays. Without those instruments, we wouldn't even know they were happening. Which adds another layer to the idea of brightness. The brightest events in the universe are not always the most obvious. They can be hidden, in a sense, occurring beyond the range of our senses, only revealing themselves through careful observation. Now, imagine for a moment being close enough to one of these bursts. Not something we would ever want to experience directly, but just to understand the scale. The intensity would not feel like a steady light. It would feel like a sudden, overwhelming surge of energy. Something that arrives quickly, peaks, and then fades. There would be no gradual build-up, no gentle transition, just a brief moment of extreme brightness, and then silence again. Now, there's another detail that connects this back to everything we've been building. Gamma ray bursts are directional. They don't emit their energy equally in all directions, which means that whether we observe one depends on alignment. If the jet is pointed toward us, we see it. If it's pointed elsewhere, we don't. So once again, brightness depends on position, on where you are relative to the source. And that reinforces a pattern we've seen throughout this journey. Brightness is not just about what exists, it's about how it's oriented, how it's distributed, and where you are when it happens. Now, as we step back and look at the full picture, gamma-ray bursts represent something important. They are among the most intense, short-lived releases of energy in the universe. They don't last. They don't sustain their brightness over time, but in terms of peak intensity, they reach levels that surpass almost everything else. So if we ask, what is the brightest thing in the universe at any given moment, events like these are strong candidates. But as always, the answer depends on how we define brightest. Sustained brightness leads us to quasars, peak brightness leads us here, and both are part of the same story. A story where brightness takes different forms depending on how energy is released. After everything we've seen so far, it's a natural place for the question to turn slightly. We've moved through stars, explosions, dense remnants, quasars, and even those brief, intense flashes of gamma-ray bursts. Each step has stretched the idea of brightness further, showing us new ways the universe can release energy. So it's only natural to wonder. So, what limits all of this? Is there a maximum brightness the universe allows? Or could something, in theory, be even brighter? Now, instead of jumping straight to an answer, it helps to slow down and look at what brighter actually means at this point. Because earlier, brightness felt simple. A candle is brighter than darkness. The sun is brighter than a light bulb. But now we're comparing things that don't just differ in scale. They differ in how they release energy, how long they last, and even what kind of light they emit. So when we ask whether something could be brighter, we have to be careful. Brighter in what sense? Brighter for how long? Brighter in total energy or peak intensity? These distinctions start to matter more and more as we move into extreme territory. Let's take this gently. Imagine you have two sources of light. One shines steadily for a very long time, releasing a large total amount of energy. The other releases the same amount of energy, but in a very short burst. Which one is brighter? In one sense, they're equal, because the total energy is the same, but in another sense, the second one is far brighter at its peak, because all that energy is concentrated into a brief moment. So brightness is not just one thing. It depends on how energy is distributed across time, and once you see that, the question becomes more open. Because in principle, you could always imagine concentrating energy into a shorter and shorter burst, increasing the peak brightness further. But here's where something interesting happens. Physics begins to set limits. Not in an obvious way, not like a clear boundary you can point to, but in a more subtle, interconnected way. Because to produce light, you need energy. And to concentrate that energy, you need processes that can gather, compress, and release it. And those processes are governed by the rules of the universe. Gravity, for example, plays a major role in many of the brightest phenomena we've seen. It pulls matter together, accelerates it, and allows energy to be released as that matter moves inward. But gravity also has consequences. As you concentrate more and more mass into a smaller space, you eventually form a black hole. And once that happens, there's a limit to how much energy can escape. So there's a kind of balance. You can increase brightness by concentrating energy. But if you concentrate too much, you create conditions where that energy becomes harder to release in the form of light. Now, there's another limit that comes from how matter behaves. When energy is released, it often interacts with the surrounding material. It can push against it, heat it, scatter it. If the energy output becomes too intense, it can actually disrupt the very process that's producing it. For example, in the case of accretion disks around black holes, there's a limit to how much material can fall inward, while still allowing radiation to escape. If the energy output becomes too strong, it can push material away, slowing down the process. So again, there's a balance. Brightness increases, but the system adjusts. Now this doesn't mean there's a single, fixed maximum brightness that nothing can exceed, but it does suggest that there are practical limits to how bright things can become based on the processes involved. And this is where the universe becomes a bit more nuanced, because instead of a single, brightest thing, we find a range of extreme phenomena, each pushing against different boundaries. Quasars push the limits of sustained brightness. Gamma-ray bursts push the limits of peak brightness. Supernovae sit somewhere in between, releasing enormous energy over short periods. Each one represents a different way of reaching extreme brightness, but none of them completely dominates in every sense. Now let's bring this back to something more intuitive again. Imagine trying to make the brightest possible light using a simple source. You could increase the power, make it more intense, but eventually you run into practical limits. The material heats up, it breaks down, the system becomes unstable. So instead of a single, perfect maximum, you end up with different approaches, each with its own constraints. That's what we see in the universe. Different mechanisms, each capable of producing extreme brightness in its own way, but each also shaped by the rules of physics. Now, there's another interesting angle to this question. Could there be something brighter that we simply haven't observed yet? Something that exists, but is either too rare, too distant, or too brief for us to detect easily? The answer, quite possibly, is yes, because our observations are always limited by our instruments, our position in space, and the time we've been looking. The universe is vast. Events happen all the time, in places we may never observe. So while we can identify the brightest known phenomena, we can't be absolutely certain that we've seen the most extreme possible case. There may be events that surpass what we currently know, but remain undetected. Now there's one more layer to this question that's worth noticing. Brightness, at these scales, becomes less about what we can see and more about what we can measure. We rely on instruments, on data, on interpretations, which means our understanding of brightest is always evolving. As we discover new objects, new events, new ways of observing the universe, the scale can shift. Something we once thought was the brightest might be surpassed by a new discovery. And that's part of what makes this question ongoing. It doesn't have a final fixed answer. It's something that develops as our understanding grows. So instead of asking whether anything could be brighter in an absolute sense, it might be more helpful to think of brightness as something with different extremes, different peaks, different limits, each defined by the processes that produce it. There's a quiet shift that happens once brightness becomes too large to compare directly. At the beginning, it felt simple. One thing looked brighter than another, and that was enough. A candle, a light bulb, the sun, each step made sense because the differences were within reach of everyday experience. But now the differences are no longer small. They're not even gradual. They span such large ranges that comparing them directly starts to feel less useful. So instead of asking which thing is brighter, it helps to ask something slightly different. Where does that brightness come from, and how does scale shape it? Because underneath everything we've explored so far, there's a common thread: energy. Brightness is, at its core, about energy being released as light. And the more energy that is released and the faster it is released, the brighter something becomes. But energy doesn't appear from nowhere. It has to come from somewhere. And that's where scale begins to matter. Let's take this slowly and keep it grounded. Imagine two fires. One is small, steady, burning gently. The other is much larger, consuming more fuel, releasing more heat and light. The larger fire is brighter because it has more energy available, more fuel, more material to burn. Now extend that idea to stars. A star like the Sun has a certain amount of mass, a certain amount of fuel for fusion. It releases energy steadily over a long time. A more massive star has more fuel, higher pressure, higher temperatures, and it releases energy at a much greater rate. So it becomes brighter. But it also burns through its fuel more quickly. So scale doesn't just increase brightness, it changes how that brightness behaves over time. Now let's move one step further. When we looked at supernovae, the brightness didn't come from steady burning, it came from collapse and explosion. A massive amount of energy that had been stored in the star structure was suddenly released. So here, scale shows up in a different way. not just in how much energy is available, but in how much energy can be released at once. A larger, more massive star can produce a more powerful explosion, so again, scale influences brightness, but in a different form. Now when we moved to neutron stars and pulsars, the scale shifted again. The objects became smaller, not larger, but their density increased dramatically. The same amount of mass was compressed into a much smaller space, and that created new conditions: stronger gravity, faster rotation, more intense magnetic fields. So even though the object was smaller, the concentration of energy became higher, and that allowed for very intense emissions. So here, brightness wasn't coming from size alone, it was coming from concentration. Now, when we reached quasars and objects like TON 618, scale returned in another form, not just in the size of the black hole, but in the amount of material being drawn inward. More mass, more motion, more energy being released as that material spirals inward, so brightness increases again. But now it's driven by gravity and motion, not fusion. And finally, with gamma-ray bursts, scale shows up in yet another way. The total energy involved is enormous, but what makes them stand out is how quickly that energy is released. Seconds, moments, everything compressed into a brief event. So the peak brightness becomes extremely high, even if the total duration is short. Now, if you step back and look at all of this together, something starts to become clear. Brightness is not controlled by a single factor. It's shaped by several things at once. How much energy is available, how concentrated that energy is, how quickly it is released, and how it is directed. Each of these can increase brightness in different ways, and different objects use different combinations of these factors. Now let's bring this back to something more intuitive again. Imagine trying to create the brightest possible light using everyday tools. You could increase the size of the source. You could concentrate the light into a beam. You could release energy in a short burst. Each approach would increase brightness in a different way, and each would have its own limits. That's exactly what we see in the universe. Different processes, each pushing brightness in a particular direction, but none of them completely dominating all the others. Now, there's another subtle point here that's worth noticing. Bigger does not always mean brighter. A very large object that releases energy slowly might not be as bright as a smaller object releasing energy quickly. A steady process can produce a lot of total energy, but not necessarily a high peak brightness. So scale alone is not enough. It has to be combined with how that energy is used. Now let's connect this back to our ongoing question. What is the brightest thing in the universe? At this point, it becomes clear that there isn't a single, simple answer, because brightness depends on what aspect you focus on. If you care about sustained brightness over long periods, quasars are among the strongest candidates. If you care about peak brightness in short bursts, gamma-ray bursts stand out. If you care about focused intensity in specific directions, pulsars and jets come into play. Each represents a different extreme. Now, there's one more detail that quietly ties everything together. Energy is always conserved. It can change form. It can be transferred. It can be concentrated or spread out, but it doesn't appear from nothing. So the brightest phenomena in the universe are always connected to large amounts of energy being transformed. Fusion, collapse, accretion, collision. Each of these processes takes energy stored in one form and releases it as light. And the scale of that transformation determines the brightness. If you step far enough back from everything we've been discussing, something begins to shift. Up until now, brightness has been tied to objects. A star, a supernova, a quasar, a burst, each one producing light in its own way, each one representing a moment or a process that releases energy. But there's another way to think about brightness, not as something produced by individual objects, but as something that changes over time across the entire universe. Because the universe itself has a history, and that history includes periods where light behaved very differently from what we experience now. So instead of asking, what is the brightest thing right now? We can ask something slightly different. Was there a time when everything was brighter? Not in isolated points, but everywhere. To begin exploring that, it helps to let go of the idea of the universe as it looks today, a place filled with galaxies, stars, and large stretches of darkness between them. Instead, imagine something much simpler, a universe that is younger, hotter, denser, and far more uniform. Because if you go back far enough, before stars, before galaxies, before any of the structures we've been talking about, the universe was not a collection of separate light sources. It was filled with energy, everywhere. At the very beginning, right after the Big Bang, the universe was extremely hot. So hot that matter as we know it couldn't exist in stable forms. Everything was in a kind of energetic state, a dense mixture of particles and radiation. Light was present, but it didn't travel freely. Instead, it was constantly interacting with matter, scattering, bouncing, unable to move in straight paths. So even though there was an enormous amount of energy, the concept of brightness as we experience it didn't quite apply. There were no clear sources, no distinct beams of light, just a kind of glowing, opaque environment. Now, as the universe expanded, something important began to happen. It cooled, and as it cooled, particles began to combine into stable atoms. This process is often called recombination, but we don't need to focus on the name. What matters is the effect. For the first time, light was able to travel freely. It was no longer constantly scattered. It could move across space in straight lines, and that moment left behind something we can still observe today. A faint glow that fills the entire universe, known as the cosmic microwave background. Now, here's where things become quietly interesting. At that time, the universe was filled with light, not concentrated in stars or galaxies, but spread out everywhere. In a sense, the universe itself was glowing, uniformly, softly, but everywhere at once. If you could have been there, not in a specific place, but anywhere, the brightness wouldn't come from a single source. It would come from the entire sky, in every direction. Now, as time continued, the universe expanded further, and as it expanded, that light spread out. Its energy decreased, its wavelength stretched, and what was once a bright, hot glow became cooler and dimmer, eventually shifting out of the visible range into microwaves, which is why we don't see it as light with our eyes today. But it's still there, a faint background signal, a remnant of a time when the universe was filled with light. Now, let's pause here and connect this back to our question about brightness, because this introduces a different kind of answer. Instead of a single brightest object, we have a period where brightness was distributed everywhere. Not intense in the way a gamma ray burst is intense, not concentrated like a quasar, but widespread, uniform, present in every direction. So in one sense, the early universe was brighter than the universe is now. Not because of individual sources, but because light was more evenly distributed. Now, as the universe continued to evolve, something else began to happen. Gravity started to pull matter together. Small variations in density grew over time, and eventually the first stars began to form. These were not like the stars we see today. They were likely more massive, hotter, and more luminous. Because the conditions were different. There were fewer heavy elements, different cooling processes, different dynamics. So these early stars may have been brighter, in terms of individual output, than many stars we see now. And as they lived and died, they contributed to the formation of galaxies, enriching the universe with heavier elements, which allowed for new generations of stars to form. Stars like our Sun, more stable, more moderate, more long-lived. So over time, the universe shifted from a uniform glow to a structured environment filled with individual sources of light, and that changed how brightness was experienced. Instead of everywhere being softly lit, brightness became localized. Stars, galaxies, clusters and large regions of darkness between them. Now there's another subtle detail that ties into this. As the universe expands, light doesn't just spread out, it also loses energy. Its wavelength increases, which means that even if the total amount of light remains, its intensity decreases over time. So the universe, in a broad sense, has been dimming. Not because light is disappearing, but because it is spreading out and stretching. So when we ask whether the universe was once brighter, the answer is yes, in a certain way. Not brighter in terms of extreme events, but brighter in terms of overall background light. More uniform, more evenly distributed. Now, bringing this back to where we are now, the present-day universe is more structured. Brightness is concentrated in specific places: stars, galaxies, quasars, and extreme events. And between those, there are vast regions of darkness. So instead of a universe that glows everywhere, we have a universe where brightness is something that stands out, something that appears in contrast to darkness, and that contrast is what makes the night sky feel the way it does: calm, sparse, even though, as we've seen, it's filled with incredibly powerful sources of light. There's something quietly remarkable about the fact that we can even talk about brightness at all on this scale. Everything we've explored so far, stars, supernova, quasars like TON 618, and even gamma-ray bursts exist far beyond any direct reach. We can't travel to them, we can't hold them, and we can't experience them in the way we experience light here on Earth. And yet, we still manage to measure them. We assign values, we compare them, we build an understanding of what is brighter than what, all from a distance, all from light that has travelled across space for years, centuries, or even billions of years. How do we actually measure brightness? How do we take all of these distant, extreme, and often invisible sources and turn them into something we can understand? Let's take this slowly, because like many things in this journey, the idea is simpler than it first appears. At its core, measuring brightness from Earth begins with something very basic. Detection. We collect light. That's it. Every telescope, whether it's small and simple or large and complex, is essentially a tool for gathering light. The more light it can collect, the more detail it can reveal. If you think about your own eyes for a moment, they work in a similar way. In darkness, your pupils widen to allow more light in. In bright conditions, they narrow. A telescope is like an extension of that idea. It gathers more light than your eyes can, allowing you to see objects that would otherwise be too faint. Now, once that light is collected, the next step is to measure how much of it arrives. And this is where the idea of apparent brightness comes back. We measure how much light from a source reaches us here on Earth. Not how much it produces in total, but how much we receive. This gives us a starting point, a way to compare objects based on how bright they appear in the sky. But as we've already seen, appearance can be misleading, because distance plays such a large role. A nearby object can appear bright even if it's not very powerful. A distant object can appear faint even if it's incredibly luminous. So measuring apparent brightness is only the first step. To understand true brightness, we need to go further. We need to account for distance, and that's where things become a little more interesting. Because measuring distance in the universe is not as simple as using a ruler or a measuring tape. Instead, scientists use a variety of methods, each suited to different scales. Some rely on observing how objects move. Some rely on known relationships between brightness and other properties. And some rely on the behaviour of light itself as it travels through space. We don't need to go deeply into each method here. What matters is the idea. If we know how far away something is, and we know how bright it appears, we can work backward to estimate how much light it must actually be producing. And that gives us intrinsic brightness. Now, there's another layer to this. Because light doesn't always arrive unchanged. As it travels, it can be affected by dust, gas, and the expansion of the universe itself. Some of it can be absorbed. Some of it can be scattered, some of it can shift in wavelength. So when scientists measure brightness, they also have to correct for these effects. They have to ask how much light was lost along the way, how much was altered, what are we actually seeing, and how does that compare to what was originally emitted? So the process becomes a kind of reconstruction, taking the light we receive and working backward to understand the source. Now let's bring this back to something more intuitive again. Imagine you're standing at a distance from a campfire. You see the light, you feel the warmth, but it's faint. If you didn't know how far away the fire was, you might underestimate its size. But if you knew the distance, you could make a better guess. You could say, if it looks this bright from here, and it's that far away, then it must be quite large. That's essentially what we're doing with stars, galaxies, and everything beyond. Now, there's another important detail. Not all light is visible. In fact, much of the energy released by the brightest objects in the universe is outside the visible range. Gamma ray bursts, for example, release most of their energy in gamma rays. Quasars emit across a wide range of wavelengths, including X-rays and ultraviolet. So to measure brightness accurately, we don't just use optical telescopes, we use instruments designed to detect different kinds of light. Radio telescopes, X-ray observatories, gamma ray detectors, each one captures a different part of the picture. And when we combine them, we get a more complete understanding of the total energy being released. So brightness becomes something we assemble from multiple sources of information. Not just what we see with our eyes, but what we detect across the entire spectrum. Now there's something quietly reassuring about this, because even though the universe is vast, and even though we're observing it from a single location, we're not limited to a single perspective. We can detect light in different forms, we can measure it, we can compare it, and over time, we can build a picture that becomes more and more accurate. Now, let's pause for a moment and connect this back to our original question. What is the brightest thing in the universe? At this point, it becomes clear that answering that question depends on how we measure brightness, what kind of light we include, how we account for distance, how we interpret the data we receive. So the answer is not just about the object, it's about the method, the process, the way we translate distant signals into something meaningful, and that adds another layer to the story. Because brightness is not just something that exists, it's something we observe, something we interpret, something we understand through the tools we build. There's a quiet moment that happens sometimes, often without you noticing it. You walk into a room, maybe after being outside, and something about the light feels different. Not brighter in any measurable sense, not dramatically changed, but somehow more noticeable, or softer, or sharper. Something shifts, and your attention catches it for just a second before moving on. That small, almost unimportant feeling is where this part of the story begins. Because after everything we've explored, from stars and explosions to quasars and gamma ray bursts, brightness has mostly been something external, something measurable, something tied to energy, distance, and physics. But there's another side to it, the way brightness feels, and that part is not written in the stars, it's written in you. Let's stay with that gently. Take the same light source, a simple lamp for example. If you turn it on in the middle of the day, it might feel almost unnecessary, you might not even notice it's there. But if you turn that same lamp on at night, in a dark room, it suddenly becomes the center of your attention. The light hasn't changed, the energy hasn't changed, but your experience of it has. And that's the first clue. Brightness, as we feel it, is not just about what exists outside, it's about how we receive it. Now, earlier we talked about how your eyes adjust to different lighting conditions, how they become more sensitive in darkness and less sensitive in bright environments. That process is automatic, something you don't think about, but it has a huge influence on how bright things appear. But beyond that, there's something even more subtle happening. Your brain is constantly interpreting what you see. It's not just receiving light, it's making sense of it, comparing it, contextualizing it, and that means brightness is always relative, not just physically, but psychologically. Let's take a simple example. Imagine you're looking at a screen in a completely dark room. The light from the screen feels intense. It stands out sharply against the darkness around it. Now imagine that same screen in a brightly lit room. It doesn't feel nearly as bright. In fact, it might feel slightly dull. Again, nothing about the screen has changed. Only the context has, and your perception follows that context. Now, this becomes even more interesting when you bring emotion into it. Because brightness is not just something you see, it's something you associate with experiences. Think about sunlight on a warm day. For many people, that kind of brightness feels pleasant, comforting, energizing. But the same intensity of light under different conditions might feel harsh, overwhelming, too much. So the same physical brightness can carry different meanings depending on how it's experienced. And that adds another layer to the idea. Brightness is not just measured, it's interpreted. Now, let's connect this back to everything we've been exploring. We've talked about objects that release enormous amounts of energy, supernovae that briefly outshine galaxies, quasars like TON 618 that shine continuously across vast distances, gamma-ray bursts that release incredible energy in seconds. All of these represent extremes of brightness in a physical sense, but none of them feel bright to you, not directly, because they are far away, because their light is softened by distance, because much of it isn't even in the visible range, so your experience of brightness is shaped by something much closer, something more immediate, the light around you, the light you interact with every day. And that creates an interesting contrast. The brightest things in the universe, in terms of energy, are not the brightest things in your experience. And the brightest things in your experience are not the most powerful. Now, there's another detail that quietly deepens this. Memory. The way you remember brightness can be different from how you experience it in the moment. A place you visited might feel bright in your memory, even if the actual light was soft. A moment might feel vivid, illuminated, not because of the physical light, but because of how your mind recorded it. So brightness becomes tied to memory, to attention, to meaning, not just to photons and energy. Now, let's bring this back to something simple again. Imagine sitting in a dim room with a single small light source. The space feels calm. The light feels gentle. Your attention is not pulled in too many directions. Now imagine increasing the brightness, adding more light. At first it might feel clearer, more defined, but beyond a certain point it becomes uncomfortable, too intense, too sharp. So there's a kind of balance in how we experience brightness. Too little, and things feel unclear. Too much, and things feel overwhelming. And somewhere in between, there's a range that feels comfortable, and that range is not fixed. It changes depending on your state, your environment, your expectations. Now, here's something worth noticing. The universe does not care about that balance. It produces brightness in all forms, steady, explosive, concentrated, brief. It doesn't adjust to comfort. It simply follows the rules of physics. But your experience of that brightness is always filtered, always shaped by your senses and your mind. So when we ask, what is the brightest thing in the universe, we're asking a physical question. But when we ask, what feels bright, we're asking something different, something more personal. Now, there's one more layer to this: attention. What you focus on becomes more noticeable. If you look directly at a light source, it feels brighter. If your attention is elsewhere, it fades into the background. So brightness is also tied to where you place your attention, what you choose to notice, and that connects back to the beginning of this journey. Because brightness in the universe can be overwhelming. There are objects releasing unimaginable amounts of energy, events that outshine entire galaxies. But from where you are in this moment, the light that matters is much smaller, much quieter. And that's not a limitation. It's what makes the experience manageable. It's what allows you to sit here, to observe, to think about these things without being overwhelmed by them. Somewhere along the way, the question itself began to change. At the beginning, it sounded simple, almost like something you could point to. A single object, a clear answer, the brightest thing in the universe, as if it were waiting quietly somewhere, just beyond the next step. But after everything we've explored, that kind of answer feels a little too small. Because brightness, as it turns out, isn't just one thing. It doesn't belong to a single object. It doesn't sit still. Instead, it shifts depending on how you look at it. So rather than rushing toward a single name, it helps to slow down and gather everything we've seen and let the answer form from that. Let's begin with something familiar again. If the question were about what appears brightest to us right now from Earth, the answer would be easy: the sun. Nothing else in our sky comes close. It dominates everything we see during the day. It shapes our entire sense of what brightness feels like. But we already know that appearance is not the whole story, because the sun is close, and distance changes everything. So if we set aside appearance and ask a different question, what produces the most light, regardless of distance? Then the answer shifts. We move beyond stars, beyond the familiar, toward objects like quasars, toward systems like TON 618, where matter falling into a supermassive black hole releases enormous amounts of energy. These are among the brightest sustained sources of light we know. They shine continuously. They outshine entire galaxies, and they do so for long periods of time. So in terms of sustained brightness, something like a quasar becomes a strong answer. But even that is not the full picture, because brightness can also be about intensity over short periods, and when we look at that, the answer changes again. Now we're looking at gamma-ray bursts, events that release more energy in a few seconds than the sun will produce over billions of years. They don't last, they don't sustain their brightness, but for those brief moments, they reach levels of intensity that surpass almost everything else. So in terms of peak brightness, these bursts stand at the top. Now we have two answers: the brightest sustained sources and the brightest brief events, and both are valid, depending on how the question is framed, but there's still another layer. Because brightness is not just about total energy, it's also about how that energy is directed. Pulsars, for example, concentrate their emissions into narrow beams. If you happen to be in the path of one of those beams, the intensity you observe can be very high. But outside that path, the same object might seem much dimmer. So brightness depends on position, on alignment, on where you are relative to the source. And that means there is no single, universal perspective. The brightest thing for one observer might not be the brightest for another. Now, if you step back even further, the question becomes more abstract. Was there ever a time when the entire universe was brighter? And in a sense, there was. In its early stages, the universe was filled with light, not concentrated in stars or galaxies, but spread out everywhere, a kind of uniform glow. So in that sense, the brightest state might not be a single object at all, but a phase, a moment in the history of the universe when light was more evenly distributed. Now, bringing all of this together, the question begins to feel different. Not what is the brightest thing, as a single answer, but what do we mean by brightest? And that's where the real answer starts to settle. Because brightness has multiple meanings. If you mean what appears brightest to us, it's the sun. If you mean what produces the most sustained light, it's quasars like TON 618. If you mean what reaches the highest intensity in a short time, it's gamma-ray bursts. If you mean where light was most widespread, it's the early universe itself. Each of these is the brightest in its own way, and none of them cancel the others out. They simply describe different aspects of the same idea. Now there's something quietly satisfying about that, because it means the universe doesn't reduce to a single answer. It allows for multiple extremes, multiple ways of reaching the limits of brightness, and that fits with everything we've seen so far. Stars, explosions, dense remnants, black holes, bursts, each one revealing a different path. Now let's bring this back to something more personal again, because throughout this journey we've been moving further and further outward, from what you can see every day, to things that exist billions of light years away, to events that last only seconds, to phases of the universe itself. And yet, all of that light, all of those extremes, are still connected to you in a very simple way, through the light that reaches you, through the photons that arrive quietly, becoming part of what you see. So even though the brightest things in the universe are far beyond your direct experience, they are still part of the same system, the same flow of energy, the same movement of light. A different kind of brightness has been with you this entire time, not the kind that outshines galaxies, not the kind that flashes for seconds and disappears, but something quieter, something steady, something so familiar that it rarely feels worth noticing. The light around you. It might be coming from a screen softly illuminating the space in front of you, or from a lamp nearby casting a gentle glow across a wall. Maybe it's daylight, filtered through a window, spreading evenly across the room without asking for attention. Whatever it is, it's there. And compared to everything we've explored, it's small. But that doesn't make it unimportant. In fact, in a very real sense, it's the only brightness that matters in this moment. Because all the extremes we've talked about, the quasars like TON 618, the bursts of gamma rays, the collapse of stars, they are far away. Their light travels immense distances, softened by space, arriving quietly, almost gently by the time it reaches us. But the light around you doesn't have to travel far. It doesn't need to cross billions of kilometers. It's immediate. It's present. And because of that, it shapes your experience far more directly than anything else. Now, there's something calming about that idea, because after moving through all those scales, all those extremes, it would be easy to feel like brightness is something distant, something belonging to the universe, not to you. But in reality, every experience of brightness happens here, in your eyes, in your mind, in the way light is received, interpreted and felt. So the journey doesn't end out there, it returns here. Let's slow things down a little. Think about how light fills a space. Not dramatically, not all at once, but gradually. It touches surfaces, softens edges, creates contrast, defines shapes. Without it, everything would still exist, but it would be hidden. Light reveals, and that's true whether it comes from a distant star or a small lamp nearby. Now, after everything we've seen, that idea becomes a little richer, because you know that light carries energy, that it travels across space, that it connects you, in a very quiet way, to things that are far beyond your reach. Every photon that reaches you has a story. It began somewhere, it travelled, it arrived, and now it becomes part of what you see. That's a simple idea, but it carries a certain weight when you pause on it. Because it means that even the smallest light around you is part of something much larger, not separate from the universe, but connected to it. Now, there's no need to hold on to the scale of everything we've discussed. You don't need to think about quasars or gamma ray bursts to appreciate the light in front of you. In fact, it might be easier not to. Because when you let go of the comparisons, something else becomes noticeable, the softness of light, the way it doesn't demand attention, the way it simply exists, allowing everything else to be seen. And that's a different kind of brightness, not extreme, not overwhelming, but steady. Now, let's return to the question we started with, just for a moment. What is the brightest thing in the universe? By now, the answer is not a single object. It's a collection of extremes, different forms of brightness, each shaped by different processes. But there's also another way to look at it. The brightest thing, in your experience, is always the light that reaches you, the light that you see, the light that defines your surroundings. And that light doesn't need to be extreme to matter. It doesn't need to outshine galaxies. It just needs to be present. Now, as this moment settles, you might notice something subtle. The way the light around you feels. Not just how bright it is, but how it shapes the space. How it creates a sense of calm, or focus, or quiet. And that's something the universe, in all its scale, doesn't take away. Because no matter how bright things get out there, no matter how extreme the processes become, your experience of brightness remains grounded here, in simple, immediate light. Now, there's no need to hold on to all the details. The numbers, the distances, the extremes, they can fade gently into the background. What remains is the idea that brightness comes in many forms, that it depends on perspective, and that even the smallest light carries a connection to something much larger. So as everything slows down and the focus returns fully to where you are, there's nothing else you need to do. Just let the light around you exist as it is. Quiet, steady. Enough.